two, two, three, four. Is it okay? Okay. All right. Hi, man, can you talk again?
Testing. 1, 2, 3. Okay.
Perfect. I'll just mute all the things on the mixer here. Okay, sure.
right. Great to see you all. I think we should get started on time because it's a tight schedule. Welcome to the SPLASH'25 2025 symposium. SPLASH' started in 2013, so this is the 13th instance of the SPLASH' symposium. Started to bring together researchers in programming languages and software engineering with educators to present their findings on tools, techniques, methods of teaching in this programming languages and software space. Kenichi agreed to be the session chair of the first session. So, Kenichi.
Yeah. Okay, the first talk is DAISY, an exercise environment for learning information modeling, and Jessica will be giving a talk.
Thank you for the introduction. So, good morning, everyone. My name is Jessica from Institute of Science Tokyo in Japan. And today I would like to present my work joined with my supervisors, Yo-Yo Chong and Hideko Masuhara, in developing an exercise environment for learning information modeling. So, when we do a problem solving through programming, it's not actually just about like writing code in order to solve the problem. So the problem solving through programming actually consists of several sub-steps, including defining data structure, creating input and output example, implementing function, and testing the whole program. So let me explain further about these steps with this simple problem statement. So here we have a problem of defining function, to define a function to calculate the area of the shape. So the first step, defining data structure. In this case, we define the data type shape because it is needed for the input of the function later, which has two cases, square and triangle. And then we can move on to creating input and output examples, and then create the function area, defining the function area, and then testing the whole program itself. So in our work, we will focus on the very first step of the problem solving through programming, which is translating the problem description written in natural languages into the data structure written in particular programming language, that we call this activity as information modeling. So information modeling is necessary to be mastered by programmer. As also what Matthias Felaisen said in his textbook in How to Design Program, it will drive the planning of the whole program. So for example, in the shape example here, the outcome of the data type shape will affect the creation of the input and output example as shown in the screen. And furthermore, it also being used in the function implementation. So in this case, the pattern matching in the function area is built based on the constructor of the data type shape that we defined before. However, despite the significant role of the programming of the information modeling, it is not really an easy task, especially for novice programmer. So in the CS undergraduate course in our institution, we observed that students often have no idea how to start the information modeling when given the problem description. And they're being overwhelmed with the programming language syntax that actually needed to define the data structure itself. So facing the challenge mentioned before, we propose a web-based programming exercise called DAISY, specifically to acquire information modeling skills. So here, using DAISY, student can bring any programming exercise problem, whether it is from textbook or from exercise in classes, to exercise with, and then inserting the problem statement in the upper left one, and then can start, once they put the problem description, they can start the exercise as seen in this quick demo. So our proposal, the DAISY, will have two main features. The first one is it offers the decomposition of the process of the information modeling into 3 steps, namely information mining, data representation, and data example, that we will explain the detail later. And also it provides the natural language-based block components to construct the data structure. So both of these features, we believe that both of these features will reduce students' cognitive load in learning information modeling by decomposing the tasks needed and omitting the programming syntax usage. So we will guide you through the process on how students could solve exercise using DAISY. And for this time, we will use the problem of defining function to count of the total resistance of a given circuit. And so the first, students can start by the information mining step, where students collect necessary information from the problem description. So using DAISY, we're guided to highlight the necessary information from the problem. As seen in this example, we highlight the keyword circuit from the problem description because we will need it as an input for the function. And we also highlighted a single resistor, series, and parallel. And also, we also highlighted the total resistance as we need them to define that's the necessary information to define the function in the later steps. And also, we need to add some information that does not explicitly written in the problem statement. So for example, for this case, we might need to add the value keyword to be able to represent the value of the single resistor, to be able to count the total resistance itself. And also we added circuit 1 and circuit 2 as series and parallel circuit will consist of these like 2 different circuits. And that's the end of the information mining step. And after we gather all the information from the problem description, we will move on to the data representation step. So to represent the data, DAISY provides like block-based data structure provided written in natural languages. So as you can see here, we provide like blocks to define data definition, constructor argument, and also like primitive data type, all written in natural language. So combining this information extracted in information mining and the data structures component in DAISY, we can create the we can represent the data representation needed here. And after we represent the data, we can create the examples based on the data representation. So in this step, DAISY provides the automatically generated templates for its constructed created in data representation. So for example, after student finish defining this data type, when move on to the data example step, DAISY will read this student outcomes and then we'll generate the template for creating data examples as seen in the screen. And using this data example templates, student can construct like a data example for its cases of the circuit. So that's the end of the overview of DAISY. And in order to evaluate whether DAISY is feasible on assisting student learning, we conducted a preliminary user study of the current version of DAISY. So this user study aims to answer these 3 research questions involving student thoughts on DAISY key features and also students' behavior and mistakes in information modeling, particularly when using DAISY. And this user study participated by the students in an introductory functional programming course taught based on the design recipe. And most of the students have some backgrounds in very preliminary computer science in Python, but most of them are not really familiar with functional programming. So the task is to solve the circuit problem, which is explained before using DAISY, and also fill in some questionnaire. So this is the result of the user study. So for the research question 1 about student thoughts on DAISY, we asked them about like how they feel about like using DAISY to assist them to do the information modeling. And from the questionnaire result, it says that most of the students found DAISY helpful, especially for the 2 key features in the step-by-step process and also provision of the block components. And we will move on to the second research question about the students' behavior in information modeling. So in order to answer this research question, we observe how students like perform the step-by-step of information modeling. So as you can see in this table, there is we can like categorize the behavior into like 3 categories. So the first one is like when student after given the problem description, they directly extract information into problem and then like adding the information that was written in the problem. And after they gather all the information, they start to do the construction of the data definition. And beside that, there is like 2 more behavior that we observe from the students. So for the second behavior, it is the same. So they given the problem description and they extract the information from the problem description. But before jumping on adding the additional information, they try to construct the data representation based on the information they have from the problem description. And then like so they do it until they do it for the information given, and then from there they add the information that is not written in the problem, and then complete the construction of the data definition. And we also observe there are like a few students who do the third behavior, which is constructing the data definition. So they try to construct the structure of the data definition first, and then they go back to the step of the extracting information to problem, and they kind of do a back-forth development of like extracting and adding the information until they finish the construction of data definition. So from this behavior, we observe the behavior in the usual case, in the conventional case, which means in the class exercise using the text-based like programming language, and we observe also the behavior when they're using DAISY in the user study. And the highlight of this finding is we found that in DAISY, it allows students to perform information modeling with more flexibility, namely like some back-forth development, and also like kind of like top-down development as seen in the third behavior. So lastly, we will discuss about like how student makes mistake in performing information modeling using DAISY. So this observation includes like the correctness of the data representation, and then how students choose the naming to be named in the data representation constituents, and also how they create the data example based on the data representation they defined before. So to answer the research question 3, we collect the outcomes from the exercise that students did in experiment. Note that we did the experiment in the Japanese version of DAISY as we conduct the experiment in Japan. So we will translate all the outcomes and naming all to English. So first, we will like to show you like that most of the students can define the correct data representation as we expected, which includes like one a data type, namely a circuit, which has a tree constructor. And in the series and parallel constructor, all the arguments are recursive, which means having the data type of circuit itself. So most of the students can do this. However, we also observe some of the mistakes in the data representation, creating the data representation. So the first one is like 6 of them create the data representation without the recursion. So they just give all the arguments of the series and parallel constructor type as like a number, whether integer or double. And then there is some of students who also did not define the recursion and not even like define the base case itself. So we will move on to the second observation of how students create the naming for the data representation constituents. So since DAISY offers the freedom of giving names in the data representation constituents, whether it is like constructor name or argument name, we found several like inappropriate naming that students use in defining the data type. So for example, 8 students use the same name for the constructor and the argument's name of all the cases. And another 3 of them using the same name even for the data type and the argument name. So we observed that this bad naming can lead students to the failure in the later steps, for example, when creating the data examples. And the last part of the third research question is about how students create the data example. So we found that among 31 students who defined the correct data representation, 15 of them created incorrect data example. So this is like a 2 representation of the incorrect data examples, which both of them involves that students forgot to write the base case constructor. And among these 15 students, like 8 of them only do this only in the innermost arguments. Hence, based on our findings in the research questions, we are thinking about doing some improvement for the current version of DAISY. So the first improvement that we think about is for giving feedback on the naming and type mismatch. So for example, for this kind of like mistakes, we could give some like error message like feedback for avoiding students creating the same name for like, for example, like data type and argument name, and also like to tell them about the type mismatch. And the alternative idea of the providing feedback is, so there is an alternative to in order to provide feedback. So since we use block to create all the data representation and data examples, we can simply not allow the insertion of the inappropriate blocks. So for example, for this incomplete like data example, we can just like allow the insertion of the circuits cases since like both of them are supposed to be like a circuit. And we can just simply not allow them to insert like another type such as a number. And the second improvement that we're thinking about is about the giving feedback of the data representation correctness. So in this case, if we just see the data representation, we know that the arguments of the series and parallel constructor are not recursive. Like, however, since DAISY allows students to input an arbitrary problem description, this level of freedom makes the implementation of correctness feedback more complicated. And currently we are brainstorming of like how to give like feedback for like such syntactically correct but like in a sense of meaning it's like an incorrect data type. We are considering we are still brainstorming on like how to give this to create this feedback, and considering the level of freedom in inputting the problem statement, we are currently considering an LLM-based feedback to check the consistency between the problem description and the data representation created. So to conclude this work, we find that novice students struggle to perform information modeling in programming exercise, and we want to assist the information modeling for the novice students. And the contribution toward this goal is to develop DAISY, a web-based block exercise environment, which has two key features of the decomposition of the information modeling process and natural language-based block components. And we were very welcome to ideas and comments for the further improvement of this work. That is all from us. Thank you for listening.
Hi, thank you for your talk. Two questions. One, I have a slight, you really need the mic, okay. All right, so two questions. One is, students generally do not enjoy being told to do steps that do not actually run. And so I'm curious, I understand you have some data, your students used it. Partly also your students know that your professor created this tool and they're expected to use it. Yeah. When you're not watching, do they use it?
Sorry, so like, we actually do watch it when they use it, like when. So
my question is, they voluntarily use this tool.
Okay, so like obviously not all of students will like voluntarily like use this tool, but I mean we just in this preliminary user study we introduced the tool and then we asked them to do it, and in the questionnaire we actually asked them like whether they want to use that.
I'm sorry, we've got to stop doing these questionnaires at Splashy. These are not research valid questionnaires, right? They know that the professor created the tool. They know they are not going to say, I'm sorry, this is an idiotic tool, nobody should have built it. They're like, they feel bad. I mean, this is well understood in research methodology, right? What you have to do is just leave it there for them to play with it and see whether over a semester they actually use it or not. Of course, they're going to say positive things in the questionnaire. If they didn't, something is wrong with the questionnaire. That's all it says.
Okay, thank you so much for your feedback. Yeah, so we're actually I mean, for this kind of tool, it is more ideal to do like some like more long-term like assessment, right? Whether they want to use it or not. And as for your suggestion, yeah, it is better to like introduce them and then like let them choose whether they want to use it or not. Thank you.
So a question from me, Patrick Jansson, Chalmers. I think this is very interesting, and there is there are different levels of the kind of things you can let the students do and not do. For example, you were saying that they name certain things wrong, and you could perhaps make the system not allow them to do that. So there is an interesting danger, which I've seen with people learning Agda, where like you fill in holes, and it's like a computer game. You fill in holes, and suddenly it's done, and you have no clue what you were doing. So if you help too much, then it's also a risk of the students not knowing what they did to get to the correct thing. So I'm wondering, have you been comparing with, I mean, it would be nice if you could sort of turn on and turn off certain of these checks to have a comparison with more and less feedback to see if the errors they make will disappear by having the help and so on.
Thank you so much. Yeah.
Patrick, long time no see. I would like to come back to Sriram's question, and that's a message for all the young authors. Whenever you're being asked a question, point one, you should repeat it, and point two, you should identify whether it is about your contribution, which was your answer, or about your assumptions, which was Sriram's question. So it's a super important point to distinguish. He wasn't asking you a question about your contribution, he was questioning your assumptions. So at the beginning, or when you're being asked the question, as you repeat the question, think very quick in your head, is it about my assumptions or is it about the contribution? Because it was about the assumptions, so of course you should not answer about the contribution.
Oh,
okay? And that's the difficulty of getting questions in a very broad audience with smart people like Sriram. Okay, that's a hit. Remember that. That will help you in the future.
yeah, thank you so much.
I have no question, just a recommendation. Thank you. Nice presentation.
Thank you so much.
Sorry, I guess I'm a little confused about what the LLM feedback is. My sense is that there is, so maybe this is the part I don't understand. I think there is a single correct answer you want students to have.
Yeah, so
So that's just a shape matching problem. You're just matching shapes. And if it's the right shape, you say good. And if it's the wrong shape, you say that's not the shape we were expecting. So for example, the fact that that shape is not recursive, that already tells you the problem. You don't need to ask an LLM whether it's recursive. You know it's not recursive.
yeah, so you stating that like I mean, when we see this, we don't need like LLM to like judge whether it is like right or not, right? Since we already like we can just see it and we can judge by ourselves. However, like so like our like ultimate goal of like developing this like DAISY environment is actually like for like especially for students to bring like so they can like exercise with like any problem description, any problem that they found like possibly like everywhere. So like we're not really like we're not really like just like stating, oh, we have like 5 or 10 like problem that you can use with this. You can use like anything, any problem statement that you want. So like we're considering this like LLM like for the consideration for like it can like it can like it is for like every problem description that, so we cannot really like for example, for this like example, we cannot really like set it in advance in the environment whether it is right or not right. Yeah. So that's the use for it.
Okay, thank you very much. The next talk is, I cannot pronounce the name of that system. Propoa.
Oh, this is yours?
An LM-based sandbox for novice practice writing purpose statements. The next talk is short paper, Evolving How We Teach Memory Models.
Yeah.
Yeah, it's my pleasure to introduce our keynote speaker, Olivier Danvy. Olivier asked me to consider to keep this introduction very short, so I'll try to do it in one sentence. Olivier shaped our understanding of programming and programming languages with his fundamental work on continuations, on interpreters, and partial evaluation. And if you needed a long introduction, you had the pleasure and the opportunity this week to attend the Olivier Fest, which was conducted in his honor at this conference. Olivier.
Keep talking.
All right. Okay. I guess the introduction is not short enough then. Any questions for Jotham is still here, right? Any questions for Jotham? Yes.
Learning objectives you have for your class are specifically?
Good to go. Thank you very much for the invitation. I'll just start by pointing out how much I take Shriram's points to heart. He gave a talk that he really emphasized was written in a researchy way, namely you have something which is measurable, which is quantifiable, towards being repeatable. Okay? So Yale and US only existed for 10 years, and I joined when it was in its third year. And so what I'm going to tell you is not reproducible, okay? And it's a best effort. See it as something anecdotal, all right? But relevant anyway. Okay, so now the way the talk is going to work is I'm going to give you the slides, and then I would like you to have the Yale and US experience for computer science. So I will overrun, okay? But so you're welcome to leave by the time, but you have to see that this is the fun part of that. So the way it works is that there will be 3 theater plays, if you like, and then you will just enact them, and then you will have the Yale and US experience as far as computer science is concerned. Okay, so that's the deal. Now I start. Imagine that you are young again. Not just that, but imagine that you were accepted at Hogwarts School of Witchcraft and Sundry. Congratulations for that, by the way. And now, with a beating heart, you're attending your very first lecture about magic. Wow. Your wand has been put on your desk with a feather next to it. And you're told to grab your wand, wave it over the feather, and enunciate Van Winchgarden grammar or something. Okay, it's a computer science joke, okay. And then the feather is supposed to levitate. And if it doesn't, it's your fault. Likewise, if you're allergic to feathers. The next lecture is about potions, and then the first thing the clearly insecure teacher does is to bully you because you do not know any of the keywords that is supposed to teach you. Okay, I do remember the book and the movie, and this is what is being described here. Gosh, can you imagine computer science being taught like that? So let's backtrack and start again. Imagine that you are young again, okay? And not just that, but imagine that you also were accepted at Yale and US College. Congratulations for that, by the way. So the motto of Yale and US College was a community of learning founded by two great universities in Asia for the world. So Yale University and NUS joined effort to create the college education from the US in Asia and to adapt it to Asia and see what comes out of it. And the experiment lasted 10 years and then was discontinued. I mean, it was cleverly discontinued. It stopped at year 6, and then there was no new incoming students. So time for the pipeline to flush out. All right, so let's backtrack and start again, but this time for good. Imagine that you are young again. Not just that, but imagine that you also were accepted at Yale and US College. Congratulations for that, by the way. And now, with a beating heart, you are attending your very first lecture about computer science. So, how computer science was introduced at Yale and US College. And the tagline is from Montaigne, a French philosopher from the 16th century, which I translated as better be mindful than have a mind full, which is kind of the motto for the rest of the talk. So I'm talking to liberal arts students, okay? They're not a computer scientist, which is not the same, okay? So it sounds like a good idea to start with Shakespeare, okay? What's in the name? So we start by defining computer science, the science of computers. Okay, I paraphrase Dijkstra, but still, astronomy is not named telescope science, if you think about it. So let's patch it. It's called computing science, what we do with computers. And there are authoritative examples, like at NUS, we have the School of Computing. And SEM is the Association for Computing Machinery, okay? But there is another objection by Peter Nauer, another Turing Award, and he objected that in saying it's not about computer science, computing is not about the processor, it is not the processing, but it is what we process, namely data. And so it should really be called data processing in the Danish datalogy, data science. Okay, this was before the statistician stepped in. So, but yes, there was another objection by a German guy, Steinbuch, French guy, Dreyfus. The big picture, we should look for the big picture. The reason why we process data, and the reason is to automate the treatment of information. And that's why it's called informatics. All right, so all in all, data science is about the things we process, computing science is about what we do, computer science is about how we do it, and informatics is about why we do it. All in all, data science, the things we process, computing science, the what of data processing, computer science, the how of data processing, informatics, the why of data processing. And amusingly, these 4 aspects, the data, the what of data processing, the how of data processing, and the why of data processing, correspond to Aristotle's 4 causes. And Aristotle was a philosopher, Greek, look at his Wikipedia page, we only have 40 minutes. But the good starting point is that both Western and Eastern philosophers were covered in the common curriculum, okay? So the import of college education in the US is not just we import Western stuff to stuff ahead of the Asians, but we do something which is actually balanced and has. Okay. So the common curriculum was the foundations of Yale and US College. People are very proud of that. It did not include mathematics. It did not include computing. And there was no reason for that. It's just arbitrary, I asked. Now is as good a time as any to quote Alan Perlis when he said that it goes against the grain of modern education to teach students to program. What fun is there in making plans, acquiring discipline in organizing thoughts, devoting attention to detail, and learning to be self-critical? Okay, sarcastic, but he has a point. Back to the common curriculum. The common curriculum was the foundation of YNC, and it featured both Western and Eastern philosophy, which was its big original point. So it was respectful of both sides and trying to make something new worldwide. So let's get back to Aristotle's four causes. The four causes is a way to distinguish aspects of things. For example, a table is a table is made of wood, that's the material cause. It's shaped into 4 feet on a plane surface, that's the efficient cause. It's done according to a design, that's the formal cause, and it's made so that you can sit at it, that's the final cause. And another example is cooking, okay? Patrick Cousteau likes to take that example to illustrate computing. So to make a dish, a cook operates over the ingredients according to the recipe. So that sentence is significant because making a dish is the final cause, is why we do that. The cook operating is the efficient cause. The cook is the actor, cooking, the operating is the action. The ingredients, that's the material cause, what they're operating over. And the recipe is the formal cause, the method to use in order to do what else we want. And so here is the Yale NUS motto yet again, a community of learning founded by 2 great universities in Asia for the world. And the first director of Yale NUS structured that motto. Okay, so it's there for everybody to see and nobody sees it. And when I say nobody, I say nobody, okay? I presented Intro to CS like that, and in week 3 I gave us an example, comment to that, and the guys from Yale NUS, man, they know how to write a lot. And they say beautiful things. And then in week 4 I pointed out 4 causes, guys, and then they were shocked. And that's the problem with modern education. Students learn what the teacher wants, and then they say what the teacher wants, and done. Okay? So the fact to meet teachers who mean what they teach and who take what they teach seriously, that's a shocker for them. And so discovering that the very motto of Yale NUS was structured around the 4 causes and they hadn't seen it was a shocker. The typical reaction was, gosh, it's true, and I should have seen it. And now they are personally challenged, and now they start to pay attention. So engaging. All right, so here we have data represent information. That's the material cause of data science. What we do with the data, that's the efficient cause, computer science. How we do it, that's the formal cause, computer science. And why we do it, so the final cause, informatics. All right. Okay, so here is an analogy with computing and cooking. And I asked that question at my job interview. So to make a dish, a cook operates over the ingredients according to the recipe. All right, the ingredients are the analog of the data. The recipe is the analog of the program. The cook is the analog of the processor. Question, what is the analog of the programmer? And now that's a question for you guys. Okay, so I'll say it again. We have just seen that computing can be defined with 4 causes, just like cooking. And the analogy here is to make a dish. A cook operates over the ingredients according to the recipe. So there's an analogy there. The ingredients of the cook are the data that we process, okay? The recipe, that's the analog of the program. Okay? It tells us what to do to operate over the ingredients. The cook is the analog of the processor. The processor is there executing the instructions. The cook is executing the recipe, okay? So in that context, where we compare computing and cooking, what is the analog of the programmer? Yes, please. The person who wrote the recipe. Okay? And that's the kind of things where the incoming students, we need to open their mind to making comparisons that make sense, okay? And build a landscape where they can actually understand. Okay, that was the first question. And nobody knows how to answer it. Good job. All right, computing and knitting. You know, you want to make a pair of socks or a hat or a sweater. And so you have little bars, and then you have a pan, and then. Okay, the data are the yarns. That's the threads made of wool, for example. The computer at large is the work environment of the knitter, the person who knits, including, for example, the knitting needles, okay, and everything around. The processor in the computer is the person who is knitting, okay? So that's kind of the same analogies, and then I ask you, what is the knitting analog of a program, and what is the knitting analog of a programmer? Yes?
Sweater, probably, and then whoever designed the sweater.
So kind of, can you like emulate the previous answer for who is the knitting analog of the programmer?
I think the program is probably the sweater, whatever we knitted. No?
Yeah. Vikram. Yeah.
The program is the knitting pattern and the programmer is the knitting pattern designer.
Right. So the programmer is the person who wrote this is how to do this is how to knit, and this is how to knit is the analog of the program. It's the things that you need to do in order to carry out the sweater. Okay, so you see, not trivial, right? But it is possible to have a uniform and unified view of computing that will kind of anchor, root, give you foundations on which you can build. And it's not obvious, as you have just discovered. So you're not alone, okay? Like everybody has that problem. All right, computing and making music is another analogy. So assume that the data are the sounds, and assume that the computer is anything that can make a sound, very broad, okay? So the three questions are, what is the musical analog of the processor? What is the musical analog of a program? There's no improvisation here, okay? There is a program. And what's the musical analog of a programmer? Yes?
The program is your sheet music.
Yep, the program is the musical score. Yes, good. Is the composer. Yes, the person who wrote the score, yes. And what's the musical analog of the processor?
Is it an instrument?
No.
Oh, the musician.
But I'm sorry?
It's the musician.
Yes. Okay. All right. Can you feel after these three questions how you have a broader grasp of the total basics of computing? And how before that you were a little blinded by details, unstructured details? Okay, so that was the spirit of why I started to introduce computer science at Yale NUS. All right, a quick word about other uses of the four causes. You can use them, believe it or not, to analyze the title of a paper, a report, or a dissertation, and then you get something out of it. And you can also use it to compose the title of a paper, report, or dissertation. So don't hesitate to ask me later. This stuff is really useful. All right, here is the pièce de résistance, a made-up French word in English. Okay, it does not exist in French. So the puzzle is, how do we introduce computer science to newcomers? Okay, which is the question that this talk is answering. So the measure of success is that the students must acquire an actionable knowledge in which they feel secure. Okay, so super high bar. The knowledge that they have must be actionable. They must be able to use it to do things, and then in which they feel secure, because all the students are panicking. All right, so the rationale is learn now and know later. And the challenge is the variety of students. Okay, some students, typically girls, say that they know nothing. Some others, typically boys, say that they know everything. So, and the great equalizer is OCaml. And here is a quote from Lee Kuan Yew, who is the founder of Singapore, about being articulate. Okay, so originally I said about English, so about OCaml, but Martin corrected me and said it's also true about Chinese. The point remains, okay, that things are not just about learning a language, because language comes with fables and proverbs and culture. It's learning a whole value system. Yeah, OKML is called by value, but that's just a coincidence. And the whole philosophy of life. Yes, totally. Okay. And the rationale is that nobody knows OKML. Okay. So that means that everybody is equal. And subsidiary point is that OKML is actually well designed. There is a design. And also, it provides a fantastic step to go from OKML to the rock proof assistant, where the types are propositions and the programs are proofs. And that was my contribution to Yale US, my only contribution to Yale US, which was to make this series of 2 courses that has propelled lots of students, which I can quantify. All right, the key pedagogy is to stick to what Aristotle and many others people said, go from what is known to what is unknown patiently. Use no forward reference, okay, except for recursion, but otherwise, present things progressively is not trivial at all, okay? And the tactics are to explain things progressively, emphasize their structure, and reuse useful things, okay? It's only useful if it is reused, okay? So to quote, to mention again something I asked Michael Adams at the end of his talk, and so all of you who use the lambda calculus as the motivator for functional programming and spend a lot of time on substitutions, there is no substitution in functional programming. It's implemented with environments, and therefore it's not reused. All the things that the students have learned about substitution, and if it is not reused, it is useless. Okay, radical, but true. So, for example, recursion, okay, which is at the end of the semester, the students should grok recursion. So in week 1, they are self-referential sentences. Which sentences are self-referential and why? And the students are completely in their comfort zone. It's about language, it's about, there's nothing technical about it, but it forces them to crystallize what it means to be self-referential in the same vein as knitting and the analogies, okay. Week 2, self-referential grammars, how to have a finite way to describe arbitrarily large data. And then from week 5 to week 13, recursive programs. And yes, there is a linguistic slant. So on a larger scale, locally, making the student feel smart works because that is very addictive. And amazingly, the other course at Yale US kind of didn't do that. The teachers stayed on top, okay, which is frustrating. On a larger scale globally, it's make the students engage in a personal adventure of computational exploration and discovery, not invention. And that's what Christopher Strachey recommended a very long time ago. He felt that computing offered opportunities for adventures of discovery. Okay, and in this computational exploration of discoveries, things make sense because they make sense, not because the teacher said so. So in other words, the key was to make room for the students' growth and watchfully get out of the way so that the students own their success. Okay, and there is a very simple way to measure that. You know the perpendicular pronoun? So it's a thing. So it's the I, okay? I or me or my. And you can measure that in a talk with the number of times the speaker is using the perpendicular pronoun. And if he's using it a lot, ego-driven. But if he doesn't, then there is room for the others to grow, okay? And the standard mantra that I used, reminder to stay cool, okay? The teacher or the speaker is not the smarter person in the room. And I remind myself that before I give a talk or I go to teach. All right, an example of pacing. There is no programming before week 3. Okay, and the students are in complete panic, those who know everything. They're in complete panic about that. Same when I teach rock proof assistant. Students say, this is terrible. In week 3, we still haven't written a proof. Okay, and they are in panic, okay? But how do you, yeah. Okay, so before that, we talk about program processors, we talk about syntax, we talk about grammars, we talk about abstract syntax tree, we talk about proof trees, huge linguistics land, so that when they start to write something, then they already know the ingredients, you know, from what they know to what they don't know yet. Example, gosh. All right. Example of structuring. So first, what the program is supposed to do. And they write unit test first to enumerate what kind of it is. And then how the program is supposed to do it, write the program. And once that's done, ta-da, test the program with a unit test. Now that worked amazingly well. Okay, so at Yale and US, the students had a breadth first range of knowledge. At the School of Computing, you have a depth first range of knowledge. Okay, they intersect, but they don't overlap. But the Yale and US students, of course, they're ambitious. So of course, they want to go for internship. Okay, so here is a typical interview in an internship. There is the interviewer and there is the student. And the interviewer asks a question which involves programming. And the School of Computing guy just takes a deep breath, puts his hand on his keyboard, and 20 minutes later of complete silence while the interviewer is bored to death, has a program that compiles. And then he has to test it. Okay. The Yale and US student, in contrast, has been drilled doesn't know what the guy is asking, because remember, he only had a semester of CS, which is ridiculous. But he has a bright smile, and then he says, let's write some unit tests. And then the interviewer say, wow, you're the first student like forever to actually do that. So yes, let's write some. And then they start to talk. So do we agree that this and that? And then as the unit tests are being enumerated on the common case, on the corner case, and blah, 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 at the end, the students has, you know, between the two ears, there is a machine learning thing that is kind of, and the student gets it. And he knows the program because he spent lots of times talking about the tests, okay? A fake quote from Einstein is fake. Okay, sorry, but it's a good one. If I had 10 hours to solve a really important problem, I would spend 9 hours thinking about the problem and 1 hour thinking about the solution. And so rushing to programming is just completely wrong. But the smart Yale and US students, they talk about the tests, they talk with the interviewer who is delighted, and at the end they get the job, and the SOC students, no. Which is absurd, because the SOC guy, he knows so much more. Okay, there is a lesson there. Okay, oh yeah, funny thing too. So they work in group, they're onto a working group, you work in the industry as groups. And also, not teaching students who will do computer science is significant, because yes, not all of them will work in computer science, but they will all work with computer scientists. So it's important that they understand how computer scientists think. And that thing was doing that. So fun thing, obviously the guys are going to do the programming because that's serious, and obviously the girls are going to do testing, okay? And of course it was hilarious when the tests were revealing bugs in the programs. And so the girls kind of built confidence, and the boys built modesty. All right, concrete support. Homemade lecture notes, comprehensive, self-contained, and they can be read forward and backwards. And I realized that by thinking about writing a piece called Demand-Driven Education, and there's this interaction about whether it's better to learn by reading the book or just by saying, I'll just do the exercise, and if I can solve the exercise here and now, I'm done. Okay? And in that discussion, there is, if the lecture notes are well written, you will learn as much by learning forward or learning backwards. And when I articulated that, I was crestfallen because I needed to rethink the entirety of lecture notes. Well, I don't do textbooks that are written like that. But this one is. All right, and last and not least here, the dimension of liberal arts, because remember, it's not computer science students, it's other people. So Nicolas Boileau, 16th century French philosopher, poet, and blah, 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 said, what is understood can be explained. Okay, and what cannot be explained is not understood. All right, Richard Feynman said that as well. So the students buy that. So, weekly reports, a midterm project, a term project, an oral exam. Not just one oral exam, 2, okay, because they have never had an oral exam, so they are not trained for that, even though I prepare them. Plus, it's excellent training for passing job interviews. All right, so tough question. Do these liberal arts things work for real computer scientists? Okay, School of Computing students. And the amazing answer is yes, they do. Okay, and I'll take that as an evidence from a student comment on nusmods.com, which is a SOC thing. And here is a quote. The weekly hand-ins force you to keep engaged with the course, for which you are not just solving problems, but also writing a full, proper report in LaTeX, where you document your learning and you reflect on the exercise. The report felt like a huge chore at the start, but I eventually realized that the reports are probably the most important bits of work I did for the course in terms of contributing to my learning. And that's the success, okay? When the student realized that by reflecting, the understanding arise, okay, fine, the mission accomplished. And it is a really nice feeling to be able to track your growth throughout the course and really feel like you're getting better each week. Okay. So see how feeling smart is addictive? Good. And once that, there's no limit what students can achieve once you're there. Here is another piece of reflection I wanted to suggest to you. So, do you agree that you learn from your mistakes? Yeah, of course, okay. Make no mistakes, you learn nothing. Good. Yet students are penalized for making mistakes. We give them homework, wrong, not fast enough, wrong. Bummer, right? So to learn from your mistakes, what I did was to offer preliminary comments that identify the beginner's mistake, congratulating the students that they made this beginner's mistake. And the cost is they have to do one more exercise, which they do, okay? So the consequence is that, okay, hold that, to prepare for the exam, the students will read not ChatGPT, not the web, not my lecture notes, but what they wrote, okay, which is amazing. And it makes students who are secure in their knowledge. All right, by the way, none of that is done anywhere else in math, in physics. Okay, the students grow into a culture of throwaway things. Nothing that I do matter because it's never reused. Plus, it's never perfect, so it's not reusable. So they are nurturing insecurity in so many ways. All right, okay, fine, cold assessment. What precedes is not new, okay? It's just a thought-out organization which is driven by empathy. I remember what it was, and I try to make it better. All right, also, it is not enough, okay, because the liberal arts students, something you cannot imagine, but they care about other things than computer science, which you can't imagine. I couldn't. Right, so yeah. How can they, okay. So now what follows is new and it did tip the scale. So that's the one new thing. Learning by enacting. So much of the material is conveyed as theater script in the lecture notes, and in the classroom, these theater scripts are read, and this is what we are going to do at the end of this formal talk. I will display 3 scripts, and I want you guys to have the Yale NUS experience. And if you don't want to read, pass, okay? But I'm sure that by the end of the talk, you will have said your piece. All right, so can you imagine that in the class, all the students voice their learning during each lecture? Okay, typically the students come to the class, shut up, and then leaves. So they are forced to be completely passive. Okay, and if they have to ask questions, like, I don't know, Bertrand Meyer says in CACM, they don't know what to ask. They just, please tell us what to do, please tell us how to do it. Our mind is, you know, the job of the teacher is that we are given students who who are both ignorant and innocent. And we have to work on the ignorance and to respect their innocence. And it is not an easy job. Anyway. So once that happens, a community of learning emerges in the classroom because all the students will have heard all the other students' voice, and they will given them they have made eye contact by passing the microphone, and kind of stunning. All right, so did this introduction to computer science work? Yes, in the sense that the computer science students became ready for the subsequent courses. And the way I did that, arriving after the course was designed, is that I humbly went to talk to each of the teachers of the following course, and I asked them, what do you need your students to know? Okay, and I will not, no, they just should not know enough Python to load library to do machine learning is not a satisfactory answer. What concept, something serious. And then I came back and I integrated that, and one of my colleagues had a funny way of starting his course. He gives a very long multiple choice question with no identification and say, have you heard about this concept? So yeah, I know it, never heard of it, and there is a grade. And then in his own work, at the end of the semester, he asks the same questions, and then he compares to see whether he has been effective as a teacher. And then he told me, it's amazing, what you do has an impact. The things have absolutely changed from the moment where you started to do that. I can see it, okay? The incoming students are more clued in. So there is that. Funny thing is that non-CS students exported CS values into their major, which was very disturbing for my colleagues. Because in social sciences, nothing is objective. There is nothing, everything is subjective. So if there is a problem, it's your fault, okay? Yeah, but it's just you who say, yo, and that's it. You roll into the flower, you're fish trying to drown the fish. But not here, okay? There's an element of objectivity. And the students scored internship on summer jobs, that's a fact. And because they are young and they are smart and they learn quickly, and anyway, in the jobs, they tell you first what you need to know. So the more open you are, the better. Okay, so from the mouth of babes, a series of quotes. An email students sent me an email, and the subject was my internship in computer vision. And the quote is, even though it was a completely new concept for me, I found myself using the logic and skills I use in Intro to CS to program the project. Okay, and the student is surprised. You're not? Not? But the student was surprised, wow. Okay, even though I'm not particularly interested in writing programs or learning programming language, the intellectual challenge found in this field is simply unparalleled. Feel good, right? But the thing is that the bar was allegedly very high at Yale College, so eliciting this kind of comments is meaningful. All right, the euphoric feeling when everything clicks and your understanding comes together is indescribable and incomparable. Okay? Addicted badge. I'm a better student because of this course. Okay, that's always nice to read. We learned a lot more about not just computer science, but we also learned a lot about ourselves. Okay, now from the mouth of baby, a reminder to stay cool. Your intro to computer science and the effort put into it was actually worth my time. Okay, so just remember, you're not the smartest person in the room. Okay, it astonishes me how much I've learned over the course of the semester. Okay, that's standard. And that one is really beautiful. In contrast to the stereotype about computer science being mechanical, the lessons and reflections contained in this report are as much a part of a beautiful personal journey as they are a part of a formal educational one. The project has been an all-encompassing experience. Multiple times in the solving and writing process, I felt transported in an agonistic trance, a deep desire to understand, truly understand exercises and my solutions. It has been most definitely a new academic experience for me, and even though it drained me of physical rest, it filled me with intellectual satiation. Okay, see, you teach, liberal arts guys, and you get that kind of literature. So much fun. All right, from the mouth of babies. I also have learned that procrastination is something that I need to get rid of. Wisdom. Lastly, I had lots of fun inserting relevant quote. Yeah, self-reference. Okay, and then the one which is the most significant one. Intro to CS was the most liberal arts course I have taken. And that came repeatedly. Okay, which, yeah, it's a pity that Yale is closed because there really was something there that could be generalized. But hey. All right, last and actually least, at Yale US College, the gender ratio was 52% female and 48% male. And the most nationalities were represented. The ambition of the college was to have a representative of each of the countries on Earth. Very ambitious. And the question which arises, was this diversity an issue when introducing computer science? Okay, you get that all the time. And the answer is not at all. And now I counter ask, why should it be an issue? It's objective. All right, conclusion before we move to the theater play. At Yale and US College, where it was unquestioned that CS is just coding, whatever coding means, students were introduced to computer science in a logical, progressive, empathetic, and rewarding way that has made them relevant and ready for the 21st century in an innovative synergy with liberal arts and science. Thank you for your time. Okay. All right, so now for the game. You're welcome to leave or to do that, but the game, and there are some students here who have done that live when they were learning, is there are dialogues, okay? And then the students just read them. So do we have a microphone? Start with Kenichi. And you just read the first line. So it's the lecture notes that start with a plea for precision, where I beg them to be precise in what they say, okay? And you can start. Halcyon, that's the representative of liberal arts.
But isn't computer science just coding?
Yep, Martin?
And what is coding?
Loki, coding is when you use a for loop.
Here's hoping that you are starting to discover that computer science is no more about coding than mathematics is merely about counting.
Okay, I just fed you a super good argument if you are told that because then you can continue from there. Yeah, sure, and literature is just about writing, right? And so on. Okay. So is it below? Yes. Okay, so this is so now we start to take off. So what is well understood is delivered clearly. Okay, that's a French Alexandrine. It has 12 syllables. Okay, so okay, this is the first week. I'm taking the students from where they are, which is liberal arts, and I'm getting them close to computer science. So have fun.
Actually, Boileau's French Alexandrine, or again iambic hexameter, comes with another one.
It does?
It does. And the second one conveys that it is actually easy to state something that we understand clearly.
Come again?
It's another instance of what and how.
I'm sorry, what is an instance?
I am sorry too. An instance is an example, an application of something general.
For example, the binomial expansion for x plus 1 squared is an instance of the binomial expansion for x plus y squared, where y is 1. And the binomial expansion for 2 plus z squared is an instance of the binomial expansion for x plus y squared, where x is 2 and y is z.
Thanks.
Also, the binomial explanation for x minus y squares is an instance of the binomial explanation expansion for x plus y squares, where y is minus y, since x minus y equals x plus minus y.
Thank you, I get it.
Sorry, I don't know how to pronounce the name.
Halcyon.
Halcyon.
you're saying that Boileau's two French Alexandrians are an instance of what and how, illustrating the measure of our understanding.
Right. The first measure of our understanding is in the first line, what we say. And the second measure of understanding is in the second line, how we say it.
And the two lines are?
Sorry, and pardon my French too while you're at it.
Ce que l'on conçoit bien s'énonce clairement et les mots pour le dire arrivent aisément.
English?
So you need to be rougher than that. English? No, American. Okay.
English?
Yes.
The second line directly translates as, and the words to say arise easily.
Which is not just good news in content, but also a French alexandrine in form.
Yeah, keep going.
Well, yes. Both the original and in the translation have 12 syllables.
Yeah, go. Translating arrive.
Translating arrivant as arise was daring, but it does preserve the alliteration.
At the modest price of considering that arise has 3 syllables, yes, but I think it works.
And you kept the adverb at the end of the first line too.
Yes. What is well understood is delivered clearly.
Yeah.
Last line.
Yes. Oh, no, I think there was already another Alexandrine.
Yep.
Well, yes. And I translated conçoit from the verb concevoir, to conceive, as understand, because that's really what Boileau means here.
Isn't deliver a bit heavy-handed?
Well, énoncer means to state.
L'énoncé du problème.
Is the problem statement. I played a bit with translating.
S'énonce clairement.
As I told with clarity, which was the contender. What is well understood is told with clarity, and the words to say it arise easily.
Right. With clarity feels more comparing than clearly here.
You need to quote, air quote. Okay, carry on.
Perhaps, but it is told with clarity also feels a bit choppy. And so in the end, I kept the two adverbs, which is also what Boileau did. Sorry. What is well understood is delivered clearly, and the words to say it arise easily.
Okay, Umberto Eco jumps in. He's the guy who made the name of the rose.
Haha. Love your journey towards saying almost the same.
Prof. Eco, thanks for stopping by. I simply love your book of collected articles to say almost the same experiments in translation about translating from
you can skip the
one natural language to another. A lot of it directly applies to implementing compilers for programming languages. It's so striking.
All right, this is the picture of the book. To say almost the same, experiments in translation. Striking pictures. Okay. Next.
Oh, the book cover of its French edition is pretty striking too.
So that was the picture.
And in the French edition, the introduction is mind-opening.
We are drifting.
More like we are drifting. No, just say it right. Okay, this is your chance.
Oh, okay. We are drifting.
Perfect.
Sorry, youthful enthusiasm and all that. This figment of imagination felt too good to let it pass by. And yes, I do know that Umberto Eco has already passed away.
You can still read his books.
All right. Okay, so it goes on. So this was the first. Second one is, so there is an exercise about composing our own definitions. And the exercise is compose a definition by genus and species, that is by type and difference, and by using some or all of the four causes. So now there is a solution by genus and species, which I will inflict to you.
Genus and species now.
Yeah, you kind of have to say genus and species now.
Genus and species now?
Yep. Martin?
Yes, that's pretty much the norm in biology.
Right. The type of the thing being defined is stated first, and then something that is specific to this thing.
No, go ahead.
Oh, you mean like Homo sapiens?
Yes. And so, for example, a werewolf would be Homo sapiens lycanthropus, a further refinement of Homo sapiens.
For another example, chocolate is defined as Theobroma cacao. Theobroma.
So, interpreters and compilers?
Perfect.
How about defining an interpreter as a processor for executing programs?
And a compiler as a processor for translating programs.
That does the job.
Perfect.
All right, now let's say almost the same thing in Latin.
Huh. How does one say program in Latin?
How about programma artis M?
Neutral, yes.
Then, as a processor executing programs, the definition of an interpreter is actor programmas agents.
Yep.
And as a processor translating or again converting programs, the definition of the compiler is actor programmers converters.
Perfect.
Effector might be a bit more specific than actor in this case.
So Annette Bianusia, that's one of the students of Peter Tiemann who actually knows Latin.
Could be.
Eugenio Moji is a guy who made monads on effects, right? So effectful monads, Eugenio Moji. Yes, carry on.
Professor Bianusia, Professor Margie, thanks for jumping into the fray.
Right, so you can see there is a running gag there. There's something going on, and there is someone relevant who jumps to it, and Mimir is a complete sucker for celebrities. So we say, ah! Okay. So, Halcyon.
So, effector programmas agents for interpreter, and effector programmas convertents for compiler.
If you guys say so.
But still.
Still?
Well, if a program is seen as a piece of code, could we say codex as the Latin for code? That makes sense semiotically.
It does. But don't let me interrupt your negotiation.
Okay, so Umberto Eco is the guy who, one of the founding fathers of semiotics. And semiotics means not like semantics, what things mean, but the social context or the cultural context of what is meant. And don't let me interrupt your negotiation. That's a quote of the book that translating is negotiating, saying almost the same. And that's done by a negotiation between the reader and the writer. Okay.
Thanks. So codex, codict M,
Masculine.
that is compatible with the Latin edition of Wikipedia about computer programs.
So if the student clicks, he arrives at the Wikipedia page. Okay.
Yes. So as a processor executing programs, the definition of an interpreter is actor, codist, agents, or again, effector, codices agents.
And as a processor translating programs, the definition of a compiler is actor codex combatans, or again, effector codex combatans, or perhaps just batans.
There you go. How about we define the 4 causes of a printer in English? You know, something concrete, nothing fancy.
You mean not a 3D printer?
Right. A line printer to print the contents of a file on paper.
That's the final cause right there.
Good. So the material cause?
Well, the paper for sure, as well as its tray.
And the ink too.
Right, and the devices to affix the ink on the paper.
And the input file as well.
Okay, that pretty much covers the material cause.
The efficient cause is all the processing from receiving the file to reading it, and from fetching a sheet of paper in the tray to affixing ink on it based on the contents of the file.
Yup.
So the formal cause?
It will be all the algorithms executed, the protocol used to receive the file, the method used to for reading it, and the strategy of affixing the ink on the paper.
And if the printer is a duplex one?
Also part of the formal cause.
And the electricity?
Well, it's an enabler, so let's say it's part of the efficient cause.
And are we done?
We are done.
Oh, we are done.
So no Latin?
No Latin.
But still.
Still?
Exit is Latin for he leaves, he goes out.
Which Anton just did.
And not just that.
Right, data is a Latin word too.
In plural form, the singular is datum.
Which is why we often say a piece of data and a data object.
Duly noted.
Okay, you see how the students end up having used lots of words, lots of concepts, by enacting a discussion. And then that gives them directions, that gives them models, that give them concrete examples. And the typical comments I get at the end of the semester or later is, I like the dialogues because they were telling me an example of reasoning, okay, and not because the teacher said that, but because I voice it, okay? And then what typically was added is that it raised, so it stated questions that I would have been not able to state, and it's mentioned questions that I would have been unable to conceive. Okay, so effective. The last one, and I'm almost done. This one is much shorter. Don't know, it's really, really, really worth it, okay? No, I know, but it's really, really short, and it will live. But you're welcome to leave.
We also have a second session.
Yeah, after the lunch.
After lunch, exactly.
Yep. So I
leave a bit of space for lunch.
Very true, but this will just take 5 minutes, and it will be completely unforgettable. You will not make me stop. So, all right. So this one illustrates the contrast between a liberal arts student, that's Halcyon. Halcyon is the mascot of the college, and typical scientists who are very pragmatic. And now there is Halcyon who is trying to do his liberal arts things, and the scientists who are doing their science things, and then we stop. Okay?
And then Juliet asked, heartbreakingly, what's in a rose?
She did? In any case, there's perfume, for sure.
And petals. A lot of petals.
Right, and when the outer ones dry out and fall, what remains is the rose.
Until all that is left is a dry stem.
With less perfume, which actually suggests that the perfume was in the petals.
I don't quite think that this is what Juliet meant by what's in a rose.
Sorry.
Two consonants and two vowels, perhaps?
So a four-letter word?
No, I mean a rose, not the name of a rose.
This is getting interesting. Do you guys need a chairperson?
Okay, Umberto Eco's rise to fame with the book The Name of the Rose, and there's a movie as well with Sean Connery. And yes. And
This is getting interesting. Do you guys need a chairperson?
Prof. Eco, thanks for sticking around.
And that's the end. Okay, so you can see that this one is also illustrating the kind of spin-off dialogues that they can be when people are bringing on their own culture and then talking about the content of the course. And at the break, okay, they talk about the dialogues, okay, and they reread them at home, okay. Can you imagine that the students read the lecture notes? One, in class because I make them read, and two, at home, so they read the lecture notes twice. Imagine that. Yeah, I know it's hard to imagine. Yep. So it awakes that interest, and it gives them lots of vocabulary. And in the course of the semester, okay, remember they come from everywhere. So the accent is extremely specific to each of them. And by the end, after a few weeks, they read English a lot clearer. And the one at the beginning say, I'm too shy. But then, no, it's fun. So why is it fun? And my model was Aaron Sorkin, who is the guy who wrote West Wing and that kind of things. And one of the typical comments they have about what he writes, like West Wing, the TV series, is that it makes the audience feel smart. Because it's smart people talking about smart things. And so I tried to emulate that, and it worked fantastically. The students engaged and then reused the words. It was really amazing to find an echo of all of that in their reports. So that was how CS was introduced at Yale and US College. Thank you very much.
All right, thanks a lot. And everyone here, we are resuming at 1:50 for the first afternoon session. See you at 1:50. Bye. All right, welcome to the first afternoon session of the SPLASH' Symposium. My name is Martin Hens, and I'll be the session chair for this session. And the first talk will be given by Kota Kumamoto on interactive learning environment for program design. This is joint work with Yo-Yo Tsong and Hidekiko Masuhara. Go.
Thank you. Good afternoon, everyone. My name is Kota Kumamoto. Today I will introduce an interactive learning environment for program design based on the design recipe. Our learning environment is called Ladder. First, let me give you a short demonstration of how it works. The students begins by entering the problem they want to solve. In this example, the problem is define a function that calculates the area of a shape. Then Ladder asked, what is the input to this function? The student answers, a shape. Next, Ladder asked, what kinds of shapes are there? The student answers, a square and a triangle. At this point, to create constructors, Ladder asks about the information each shape has. The student answers saying the length of a side for a square and the length of the base and the height for the triangle. In this way, all the necessary information is collected. Ladder automatically generates the data definition code in Scala, like this. This is how Ladder works as an interactive learning environment. And importantly, because Ladder uses an LLM, it can handle any problem students choose to work on. This means Ladder does not require model answers from teachers. Next, let me talk about the motivation behind this work. The design recipe breaks program design into clear steps, such as defining input data and making a function template. With an instructor, this recipe helps students move from the problem statement to good code. But in the absence of an instructor, students may face several issues. First, with abstract description of the design recipe, they may not know what to do at each step. Second, if they don't have enough knowledge of the programming language's syntax, they may not be able to write the outcomes at each step in a grammatical way. Third, when there is no feedback on the intermediate outcomes, they cannot tell if they are on the right track. To address these issues, we propose Ladder, a natural language dialogue-based learning system. It uses an LLM so that students can solve problems on their own without relying on an instructor. Ladder addresses the issues in 3 ways. First, it gives step-by-step guidance by asking questions piece by piece. Second, it accepts natural language input and generates code with proper names for functions and variables. Third, it provides feedback at each step, checking the student answers against the problem statement. I will explain these features in more detail later. This is the interface of Ladder. On the left, we have the code preview area. We have the dialogue area. In this area, students interact with Ladder using natural language. On the right, we have the code preview area. This area shows the code that Ladder generates based on the students' responses. We already demonstrated how Ladder works, so here, let me just highlight the simple learning flow it follows. First, students enter the statement of the problem they wish to solve. Next, the student goes through the steps of the design recipe. At each step, the student interacts with Rudder using natural language. When the step is complete and all necessary information is collected, Rudder generates the code based on students' responses and shows it in the code preview area, like this. As you can see, Rudder automatically generates the type name, shape, and the constructor names, square and triangle. The student repeats this process through to the testing step. So far, we have implemented all the steps except the testing step. We realize this running flow by building a custom GPT using OpenAI's MyGPT service. In particular, to guide students step by step in natural language, we specify the detailed conversation flow in the system prompts like this. Rather, what is the input to this function? Student XX. Since the student input is unknown at this point, we use placeholders like XX. And in later term, Rudder can reuse XX in its questions, like let's define a data type to represent XX. All of these system prompts were actually written in Japanese. After implementing Rudder, we ran a simple user study to whether students can use Rudder smoothly for program design. The participants were 42 second-year undergraduate students in our institution, and their task was to design a program using Rudder and then fill out a questionnaire. We used, in this user study, we used this problem to define a function that calculates the perimeter of a shape. At this stage, we focused on evaluating the usability of Rudder rather than measuring its running effect. This bar chart shows the 42 participants performed when using Rudder. As you can see, 22 students completed their program design successfully. 10 students experienced broken dialogues that went off the intended flow. 4 due to student-side input issues, and 6 due to system malfunctions. The remaining 10 cases include incomplete dialogue logs or access restrictions during use. Here, I will share 2 observations we made from our analysis. We looked at how students actually interact with Rudder and how robust the LLM-based guidance was. First, many students frustrated by dialogue granularity. Second, in many cases, Rudder was able to handle unexpected responses from the students. Let's start with the first observation. In the current version of Rudder, the dialogue is designed to ask very detailed questions in order to support students' understanding. As a result, in the function template step, Rudder asks questions to confirm the content from the data definition step. And in the data example step, Rudder asks about each argument one by one. These detailed dialogues were not always welcomed by students. We often saw responses where they tried to avoid the tedious back and forth. There were 2 main patterns. First, some students asked Rudder directly to skip the detailed questions. For example, in the data definition step, when Rudder asked what kinds of shapes are there, the student replies, rectangles and triangles. That's all. Please move on. Second, some students gave several answers at once, predicting the next questions. For instance, in the data example step, when asked about the length of the first side of a triangle, a student answered all three sides together, 3, 4, and 5. And in the questionnaire, 16 students also mentioned these issues. Based on these observations, we are now considering ways to adjust the granularity of dialogue. Next, let's look at the second observation. We found that Radar could respond flexibly to students' input. Here is an example from the data example step. When a student gave all three side lengths of a triangle at once, Radar confirmed the intention by asking, so side 1 is 3, side 2 is 4, and side 3 is 5. And then Radar skipped the unnecessary follow-up questions and moved on to the next step. This shows that even though the dialogue is fixed in detail, Radar can still make use of the flexibility of the LLM. Next, let me share some interesting results from the questionnaire. We asked which steps felt easier with Radar compared to running without it, and why they felt that way. The most popular step is the data definition. One key reason is that Radar automatically generates English variable names in code, and students found this very helpful. This is an unexpected benefits, and it may be especially useful for students who are not native speakers of English. Next, let me talk about 3 directions for future work. First, we plan to implement multiple interaction levels. As I mentioned, the current dialogue of Radar sometimes feels tedious. We plan to let students choose the dialogue levels based on their proficiency. For example, using cursor questions, answering in code, or directly editing code. Second, we would like to revisit the implementation. While Radar can handle flexible dialogues with an LLM, in some cases, the interaction completely broke down, and we even saw prompt leakage. To address this, we are considering redesigning parts of the implementation, such as using manual control to fix certain parts of the dialogue. Third, we aim to provide appropriate feedback. In our user study, some feedback worked well, like a real instructor, but in other cases, Radar simply gave the correct answer. We plan to improve this so that more of the feedback supports students in revising their own answers. Finally, let me briefly introduce 2 related systems. First, SPLASH'25 TARC is an AI tutor that helps students with programming tasks by answering their coding questions. Like Radar, it uses an LLM to assist students, but unlike Radar, it focuses on coding rather than program design process. Second, Mio is a block-based learning environment that allows students to practice program design following the design recipe. Compared to Rudder, its feedback feature is more limited as it does not use an LLM. Let me summarize our work. We proposed Rudder, an interactive learning environment based on the design recipe. We hope Rudder can grow into a useful tool for learning program design and help students become better problem solvers. Thank you for listening.
Do you have questions for Kota?
Thank you so much for your talk. I was wondering, so oftentimes in a class, we have students with different levels of understanding of the coursework, of expertise. Do you think the level of granularity has some connection with the experience that these students have, or are there any other factors that may contribute to having all these different levels of granularity to help them understand how to program?
Thank you. So,
I can repeat the question. So do you think so the question is if the level of experience of users may have an impact in the way we, for example, design the different levels of granularity in Ladder.
So let me try asking this in a slightly different way. If I'm a very experienced student, I might get very annoyed if you ask me lots of small questions.
Yeah.
If I'm a very I'm a student who's struggling a lot,
Yes.
and you ask me very big questions, I won't know how to answer them. Does that make sense?
Yes.
So I think one way I would phrase the question is, shouldn't you make the questions based on the student's ability so far? Does that make sense?
That is how measure the student levels?
Well, that's your problem, not ours. That's why we're on this side of the stage and you're on that side.
So.
I'm Koso, so maybe I would add some answers. So what he's currently thinking is just to offer multiple level of granularity so that the student can choose their own preferences, but it might be also nice to think about to measure the student's abilities and automatically select that. So.
There's a long tradition of adaptive systems that do this, right? The entire adaptive tutor literature and so on. So we have ways of doing it, yeah.
All right. Other questions? Yeah, okay.
Thanks for the talk. It's a question for you on the DAISY talk this morning. You have 42 students, and you have 42 students.
Yes.
Why? Is it like a standard number in Japan? You have 42 students per classes. Oh!
Yeah, thank you for the talk. So, how do students know how to answer the question, what is the input to this function? In the book, Animated Problem Solving, this question is answered by teaching students how to perform an extraction step over similar expressions. So how do you guys approach answering this question?
Sorry, could you repeat the question? Sorry.
So, how do students know how to answer the question, what is the input to this function? In the book, Animated Problem Solving, this question is answered by teaching students how to perform an extraction step over similar expressions. So, how do you guys approach it? Or how do your students answer the question? What is the input to this function?
Your question is, what is the correct answer?
How do your students answer the question?
Okay. The many of them answered shape.
So I believe in one of your steps of the design recipe, you asked, you guys are asking the students, what is the input to this function? So how do your students know how to answer that question?
Sorry, the question is?
How do what is the input to this function?
What is the input to this function?
Yes, so like.
Original question. So the question is, how do students know how to answer the question, what is the input of the function?
Okay. The students knows from the problem statement. So,
I guess, so I'm teaching that course. So in that course, every time we develop a function, we go through all the steps of the design recipe. So the students should be able to answer this question if they understand the design recipe correctly.
Yeah, so it's a question of the scaffolding, right? Does it answer the question? Do you have a follow-up question? So it's.
I'm just more curious about, I guess, the difference in teaching and pedagogy, because within how we teach the course in the design recipe, students are taught to perform an extraction step over the similar expressions to figure out the inputs to their function. So how do you guys teach students to figure out the inputs to their functions?
Is this extraction part of the recipe?
It's usually implicit, and since this is a very introductory course, the functions students develop are usually very simple, so it's easy to find the input. But on the other hand, in this experiment, we had several students answering something like the size of something like that, instead of saying shape.
Thank you.
Okay, yeah, let's thank the speaker again. And the next talk is given by Yo-Yo Tsong, a co-author of the previous talk, on Continuations for All, Language Design Considerations for Accessible Continuations. And this is joint work with Philip Strömbeck and Katsuki Ikemori.
All right, thank you. So I'll be presenting our work making continuations accessible. So this is joint work with my collaborator in Sweden, Philip, and our PhD student, Kazuki. So continuations are an important concept for students and programmers to master. So if you open a major textbook on programming languages, you typically see topics such as CPS and CoCC covered. And also, a lot of programming languages nowadays provide support for programming with continuations, so people have more opportunities to use or see continuations. However, in existing languages, continuations are not supported in a very beginner-friendly way. So let's consider this Rocket program that uses the shift and reset operators to manipulate a continuation. To a beginner of continuations, it is not easy to guess what the shift operator does from its name. And also, there is usually no way to see the content of a captured continuation. And it could be challenging to figure out how a particular use of a continuation affects the evaluation of the entire program. And to provide a better learning experience, we are developing Pirate Cont, an educational language for learners of continuations. As the name suggests, Pirate Cont is an extension of Pirate, which is a functional scripting language designed for introductory computing courses. We picked Pirate as the basis of our language because Pirate has a familiar Python-like syntax, and it can be used as an untyped language, and it also comes with a web editor that works on the browser. And we extended the Pirate language with constructs for manipulating continuations, and we extended the Pirate web editor with step evaluation functionality. So let me give you more details of our extensions. In Pirate Cont, we provide 3 kinds of continuation constructs. The first one is grab and delimit, which behave the same as what is called shift 0 and reset 0 in the literature. And then we have send and run, which are a minor modification of fcontrol and run supported in Rocket. And we have algebraic effects and handlers. So the grab and delimit operators literally grabs and delimits a continuation. So here we are using these operators to simulate a read-only effect. And since we are calling the read function in the context something plus 2, this captured continuation k will be something plus 2 surrounded by a delimit operator. Okay, so the program will evaluate to 3. And the send and run operators have the similar functionality with grab and delimit, but its syntax is closer to exceptions and their handlers. So the send operator sends a signal to capture a continuation, and the run operator handles that signal by providing a continuation. So in this case, we're using this send operator in the context something plus 2. So again, the continuation is plus 2 surrounded by the original run expression. And algebraic effects and handlers can be thought of as a version of send and run with a more convenient user interface. So on the left, we are defining the reader effect, which has the read operation taking in no arguments. And on the right, we are handling the read operation with a handler that interprets the read operation as resuming the continuation with 1. So, as before, this captured continuation k includes the addition and the original handler. So these are the 3 continuation constructs we provide in Pirate Cont. And to help learners understand the behavior of these constructs, we augmented the Pirate editor with a stepper. The stepper shows all the evaluation steps of the program, just like Dr. Rocket's algebraic stepper. So in the case of this example here, the stepper shows the read function expands to a grab operator. And then this grab operator grabs a continuation represented as a lambda expression. So those curly braces represent lambda in pirate, and the $sign is the input of the continuation. And then this continuation call is treated just like a function call, and then when the body of the delimit becomes a value, the delimit operator disappears. Okay. So that's our pirate count language. And using pirate count, we taught a graduate course on programming language theory. The course consisted of 14 lectures covering CPS, grab delimit, send run, and effect handlers in this order. And last year, the course was attended by 55 students. Most of them were familiar with Python and Scala, and 11 of them had no prior experience with functional programming languages. In the middle of the course, we investigated students' perceptions of our three kinds of continuation constructs. Specifically, we asked the students to tell us how easy it is to understand and use the three continuation constructs. So let's look at students' responses on the ease of understanding. There seems to be no clear winner here. But we can see that the distribution of students' responses for grab and delimit is more even than the other two. And we presume that this is due to the unique syntax of grab and delimit and the fact that the grab and delimit were introduced first in the course. And when we looked at the reason behind students' responses, we saw students saying that when using grab and delimit, we can reason about program in a local way because the use of the continuation is written in the capture side. But when using the other two constructs, we need to go back and forth between a handled expression and the handler. And next, we look at the students' responses on the ease of use. This time, effect handlers seem to have received slightly more positive responses. And the reason, the main reason is that effect handlers have a high-level syntax and it's easy to read, whereas grab and delimit and send and run are a little bit too primitive. And based on these results, we can conclude that different continuation constructs are suitable for different purposes. Like grab and delimit are suitable when the focus is on understanding the behavior of programs that manipulate continuations because they allow local reasoning. On the other hand, effect handlers are suitable when the focus is on building interesting programs that uses continuations because it's easier to program with them. In the same week, we also collected students' opinions on existing languages that has support for continuations. And to do this, we prepared an assignment where students were asked to write a non-deterministic program in 3 languages. And these 3 languages include OchaCamel, which is an ML-style language with shift and reset operators, and Racket, which is a Lisp-style language with F-control and run, and Effect, which is a Scala-like language with effect handlers. And then we asked the students to report what they liked and didn't like about the 3 languages compared to pirate count. So let's begin with the students' comments on OchaCamel. Many students liked the concise ML-style syntax, but they had different opinions about the syntax of function application that uses spaces rather than parentheses and commas. And students generally didn't like the names shift and reset as much as our names grab and delete. And next we look at students' comments on Racket. Not surprisingly, many students, or almost all students, didn't like the parentheses and the prefix notation. And in Racket, the handler of a run operator is written as a lambda expression, and we had both positive and negative comments about that. So some students said it's good to reuse some existing syntax, but other students said the lambda expression makes the handler harder to read. And again, the students didn't like the keywords f control and percent as much as our keywords send and run. Okay, now we look at the comments on effect. So the effect language received most positive comments. And that is probably because effect is close to Scala and many students were already familiar with Scala. Interestingly, many students mentioned that they liked the use of curly braces as block delimiters. And in effect, we use the resume keyword to call a continuation and do keyword to call an operation. And among them, students liked the resume keyword because it's descriptive, but they had different thoughts about the do keyword. So for some students, they found it beneficial to distinguish between function calls and operation calls, but for other students, this do keywords doesn't mean anything special, so maybe it's not worth writing it. Based on students' comments, we can derive some design principles for a good continuation language. First, we should design the syntax so that the language looks close to conventional languages. And in particular, the syntax of application and block delimiters is very important. And second, we need to use descriptive keywords for continuation constructs so that students can immediately see which construct does what. And thirdly, it's a good idea to use a custom syntax for constructs that introduce bindings like grab and handlers instead of reusing primitive lambda expressions. At the end of the course, we ask the students to share their overall experience with pirate cont through anonymous survey. So many students liked the fact that pirate is similar to Python and it's untyped by default. And they also liked our intuitive keywords for continuation constructs as well as the step execution facility. On the other hand, we received some negative comments on the pirate original syntax, which requires the end keyword for each block and the spaces before and after binary operators. And we think that these negative comments stem from the gap between pirate audience, which is beginners of programming, and our students who already have some experience with programming. We also asked the students about their use of the stepper. About half of the students used the stepper at least once, and those students found the stepper useful for finding mistakes and understanding the three continuation constructs. So based on these results, we can conclude that the overall design of pirate cont is on the right track, and the stepper is a good tool to have in a continuation language. And to further improve the language, we could adjust the syntax to more advanced programmers. We are still developing the pirate count language, and in the future, we plan to provide multiple visualizations of continuations. So currently, the stepper shows continuations as lambda expressions, but we can also use some other representations, such as a stack-like representation, and let the student choose the one that works best for them. We are also interested in incorporating the notion of language levels. So the idea is that we start from restricted use of continuations and gradually relax those restrictions. And maybe that would help us prevent some mistakes or provide better error messages. To conclude, we think that we can make continuations more accessible by designing an appropriate language. Our pirate count language is available on the web, so you are all welcome to try it out. Thank you.
So at the beginning, you had a poll on which style of continuations students like best, right? At the beginning of your slides.
Mm-hmm. Which styles or which constructs? Maybe.
Which construct? It was
like this?
Yes. Did you have a way to collect, I guess it would be correlational data between the different questions? Like, do the students who think grab and delimit is hard also think send and run and effect handlers are hard, or is are they expressing a preference?
Okay, we could have done that, but we did not analyze from that perspective. But yeah, I will look at the data again. Yes, thank you.
More questions? Yes.
So as you know, I love this work. Other than the syntactic choice for the binding construct, other than that, I totally love it. I do actually have several questions. I don't think you should study this correlation because I don't think this data actually means anything. Okay, there's we have a lot of experience in education research where basically what people think is hard and what they actually don't do well at are completely different things. Oftentimes, people think something is easy because they haven't actually understood it. Okay, until you know and it's like, yeah, it's totally easy. And then when you try to actually demonstrate their understanding, they do very poorly on the easy thing and vice versa. There are so many phenomena here, cognitive and pedagogic phenomena, that you can squeeze the data till it screams and compute correlations and none of it will mean anything. Right? I would encourage you to think about taking the research to making more of a research project because you want to do this seriously.
Yeah.
The other two comments I had, I've been starting to think that it's actually really important to approach continuations through the lens starting out of generators, even before you get to all of this. Because generators are basically local continuations. Okay, and in fact, one of the things I do in my course is we study the difference between Python and racket generators because they're semantically very different and there's really interesting design choices in each one. And even just understanding that and understanding that racket generators pretty much are like a call CC, but Pythons are not, and why they're not, there's very interesting reasons why. But also it's a much lighter weight form of continuation, and it's one that they have to know. You can't program in anything today without understanding generators. Right? So they're going to have to understand it. It's an accessible topic. They should know it. And it's a lighter weight introduction to all of these other things. So I would encourage you to add generators as the first step. Maybe it goes really quickly. I suspect you will actually find various misconceptions, because I've been finding various misconceptions that people have about generators. Okay? And the third comment I wanted to make related to this is the stepper thing. as you might know, I'm a strong disbeliever in Dr. Rackett's stepper. I hate it. And the idea that somebody would re-implement it in another language and put it in Pirate, just like, oh my God. And because it's broken in so many ways. And we've got a stepper that basically uses local, the two things that are broken are, one is it has the global evaluation context. And so anytime you write a larger computation, you get penalized for it. Because the context just grows bigger and bigger and bigger.
Right.
If you ever use any data, you get penalized for it because of substitution. But we don't need either of these things. We can use local evaluation contexts and environments. And now all of a sudden, like I have like undergraduates who are never going to take a grad programming language class, who have no trouble with evaluation context just with those two small changes. So if you're interested, happy to show you some ideas and data on that.
Thank you.
All right. Yeah, I know. That's great.
Oh, great talk. So I guess keying off of Shriram, I have a question in the back of my head, less to do with the data and more what you've observed about students and how they're thinking and conceiving of this kind of like nonlinear control flow. And so in the ed literature, we have something called a notional machine, which is how people think of kind of what?
Yes.
Okay, so I guess my question then for you is, do you explicitly use the stepper as kind of the teaching notional machine in the class? Is it an explicit kind of connection point, or is it, is there and so I guess my ultimate question is really, is there a disconnect between how students perceive how continuations work and then perhaps how the stepper is the official way you want them to sort of think about it?
Yeah. So in the course, we just use the stepper for the first few lectures. So this is not like the notional machine for continuations, but we did actually not survey, but an activity where students were asked to visualize a certain continuation. And it's a completely free-form question. And quite a lot of students draw a stack-like structure. And we also had some more fancy visualizations I can show you later if you're interested. But I think the stack representation could work well, especially for those students who are familiar with the low-level coding stuff. Yes.
What are the examples that you give the students throughout the semester? Which programming example do they study? Which programs?
So we started from exceptions, and then non-determinism, like binary choice. And then we actually did the generator example. And lastly, state. Yes, these examples.
Thank you.
Thank you.
Any more questions? Wow, that's great. Thanks
Thank you.
again. The next speaker is Mikhail Barash, and the title of his talk is Involving Students in Design and Implementation of ECMAScript JavaScript Proposals.
Welcome to the last session of the day and also the last session of the week, I guess. So the first presentation will be by Andres and by Tiana about derivation visualization for context-free grammar design.
Okay. Hello, everyone. My name is Tiana. I'm a PhD student at the University of Washington.
And I'm Andres Garced. As a quick aside, I'm actually looking for PhD positions right now, so if you're looking for any students, feel free to talk to me after the talk.
And today, we're going to talk about a derivation visualization for context-free grammars. This is joint work with Marco Morazan from Seton Hall University.
Context-free grammars are widely used to describe the syntax of modern-day programming languages, and thus students are expected to learn how to design and implement these grammars. This is an example of one such grammar. Oh, goodness. You can see on the left here, and it's written in the typical notation that you'll find in most flat textbooks today. Students are also expected to learn how to derive words in the languages of these grammars, and you can see one such example of this derivation on the right. Flat courses teach students how to do a variety of different things with context-free grammars, but our contribution today is going to be focused on the highlighted points here, designing, implementing, validating, and verifying grammars, and deriving words in the language of these grammars. Students struggle with context-free grammars for a variety of different reasons. One is that they don't know which production rule to apply when deriving a particular word, and the reason for this is that there's nothing inherent in the definition of a context-free grammar that helps them decide which rule to apply, and thus some students might think that all the rules ought to be applied. Another issue is that some students have been trained solely in deterministic programming and thus don't yet see the relevance of non-determinism in their CS education. And finally, word derivation is inherently recursive, and some students are uncomfortable with recursion and thus developing recursive sets of production rules. Our contribution today is a new tool to visualize grammar derivation that includes facilities to visually validate invariance of that grammar. And we would like to address the following research questions. Does the visualization tool help students better understand word derivation, their understanding of non-determinism? Does it help with the development of correctness proofs? And does it help them with the debugging process? Thus far, we've been helping students design and implement grammars in FSM. FSM is a domain-specific language embedded in Racket, where students can implement, validate, and verify grammars of machines. Non-determinism is a built-in feature, so students don't have to implement it themselves. And because it's a programming language, they can write unit tests to get immediate feedback on their designs, thus lessening the burden of questions on their professors and teaching assistants. It's also tightly coupled with a design recipe. These were pioneered by Felizen and others for the Intro to Program Design Classroom and has been extended for context-free grammars by Morazan. To give you an idea of what this would look like in FSM, here we have the grammar that you can typically find in a flat textbook on the left, and the equivalent in FSM. So we have the constructor make CFG, and it takes as input non-terminals, terminals, production rules, and a starting non-terminal. Here we can see the design recipe for context-free grammars, and at a high level, what we'll have the students do is pick a meaningful name for their grammar, define syntactic categories for each of the languages and sub-languages needed for this grammar, to develop production rules based upon those syntactic categories, and to write unit tests for it, finish implementing it and validate their design by running those tests, and to verify their grammar through the use of invariants. This is what it looks like to implement the first 6 steps of the design recipe. You can see at the top we have the language defined in the comments, and below that the syntactic categories. So because S is a starting non-terminal, its syntactic category is the language that we're designing for, and because there's 2 sub-languages in that language, we associate a non-terminal with each of those, A to the M, B to the N, and C to the M, D to the M in this case. You can also see the constructor below that, and some unit tests at the very bottom. Here there's 2 types of unit tests, one for check derive and check not derive. They both take as input a grammar and an arbitrary number of words, and in the case of check derive, it validates that those words are in the language, and for check not derive, that they are not in the language.
So this, it would be a result of step 7 of the design recipe, and I would like you to pay attention to this one because we are going to be mentioning it later in the talk. So in step 7, students are required to develop invariant predicates for each syntactic category. This is an example of one such invariant predicate. So the predicate just takes as input, okay, I have to point that way, takes as input a word and returns true if the given word is in the language that the syntactic category represents. So in the case of E invariant, it would be A to the N, B to the N. And the only thing this code does is takes all the A's from the beginning of the word, takes the B's that follow, appends them and check if they're equal to the word, and compares the lengths of A's and B's. And we can also use unit testing to test these invariant predicates with different words to validate that they've written them correctly. So we can write invariant predicates for A and for F invariant, for S and F invariant, I'm sorry. So when it comes to designing and systematically approaching designing grammars, FSM does provide students with some useful features. But when it comes to word derivation itself, so far, FSM has only provided them with this observer called grammar derive, which takes as input a grammar and a word, and it just returns the leftmost derivation of that word, of that grammar, just written in the standard textbook notation. And this is kind of hard to read. If you're dealing with a larger word, you would have to kind of trace manually where each non-terminal gets substituted, and it gets very messy very quickly, especially if you're a beginner. So our contribution for today addresses this issue. It's a visualization tool that performs a stepwise derivation, and it has an option to visualize invariant predicates. This supports leftmost, rightmost, bi-level left, and bi-level right derivation. And instead of just talking about the tool, I'm just going to show you what it looks like and how you can use it for debugging. So let's see if I know how to do this. Perfect. Okay. So can you see this? Okay. So this is the grammar that you've just seen for the language A to the N, B to the N, C to the M, D to the M, just as it was written in the slides. And we're going to run the visualization with the grammar and the word AA, BB, triple C, triple D. So once we run the tool, this is what we get. So every FSM tool consists of 3 main components. The main visualization graphic, in this case, it's just going to be the derivation tree. Informative messages, which provide additional context on what's happening in the main visualization graphic, the last step taken. And finally, the instructions that we can click on or just execute on the keyboard that drive visualization forwards, backwards, and have zooming and dragging capabilities. So let's move the visualization one step forward. Once we do that, a single production rule is applied, and we have an informative message telling us the last rule used. It is color-coded to match the main visualization graphic, and as you might see if I step forward a few times, only the last production rule applied gets color-coded so students can immediately see on the graphic where the derivation tree extended. We have an informative message for the word that we are trying to derive and the current yield of the derivation tree, so we can see how the yield changes into the word that we're trying to derive, and eventually, once they match up, we know that the derivation is concluded. So this is what the tool looks like, but now I'm going to show you something cooler, which is how to use it for debugging. So this is a buggy grammar written by a student for the language A to the I, B to the J, C to the K, where I equals J or J equals K. So you can see here 2 error messages. If we run it again, same ones are going to show up. If we click on the X's, we can see exactly which words errored out, and we can see a step of the design recipe that hasn't been successfully completed. So these are special error messages called recipe-based errors that refer you to the step that you might have done wrongly. So step 6 is just run the test, see if everything runs, and redesign if necessary. So we can see here that this grammar derives the following words that are placed in check not derived, so they shouldn't be derived by the grammar. So to debug this, we can run the visualization tool with the word, say, BBBCCCAA, and we can give it as input the invariant predicates that the students have written in the step 7, so they know, or they can see where the bug is. So if I go here and run this with the word, we can see, starting non-terminal, we get this new message that tells us all invariants hold because we haven't yet executed any production rules. But if we move forward, we see that the S invariant doesn't hold. So just based off of this, we don't have a lot of context about why S invariant might not hold, because S invariant should just produce the words in the language. But if we find the bottommost red node, maybe that would tell us where the bug is. So if we keep stepping, we can see that the B invariant also doesn't hold, but the E invariant holds. So presuming that the invariant predicates are written and tested correctly, now we know that E generates what it's supposed to, and even if we keep stepping through, everything is fine on the left-hand side of the tree. F invariant also seems to hold, so presuming that the invariant predicate is written correctly, F is generating what it's supposed to. So the bug could be somewhere in the B invariant. So let's move this for a second and go back to our grammar. So the bug says that it's somewhere in the B invariant. The B invariant is supposed to generate words in A to the I, B to the K, C to the K. And the production rule for B says that it generates a concatenation of E and F. Now, we know that E and F both hold, so let's see what they actually generate. So E generates B to the K, C to the K, and concatenated to that would be F with A to the I. And this doesn't match up what the B invariant should be generating. It seems like they mixed it up. So if we go back to the rule for B and correct it to FE instead of EF and run this, it seems like we've solved the bug, but let's check with the visualization. Doesn't even run because the word is not in the language of the grammar. So that's a good sign. Now, we still have one more error message, which is telling us that this word is being derived, that apparently shouldn't be derived. So let's run the visualization tool with that word. If we just click here, it's going to tell us exactly where it is. So we're just going to replace it and give invariant predicates as input. So once we run this, I'm just going to complete the tree in one step so we can immediately see where the bug is. All of the invariants seem to hold. So S generates words in the language, so seemingly this word AA, BB, CC is in the language. So if we look back at the definition, it says that it should be A to the I, B to the J, C to the K, where I equals J or C equals, or J equals K. And this word, AA, BB, CC, fulfills that condition. So it could be that the student might have mixed up the definition of or and exclusive or and just written the test wrongly, which is what I suspect this is. So if we move this to check derive and run it, it's all good. So now imagine if you went through this entire debugging process, even with the visualization, without visualizing the invariant predicates. It would have taken much longer to find where the bugs are, and even if the bug is complicated to debug, or even if you need a complete redesign, you significantly cut down on the debugging time by being able to just glance over the derivation tree, find the bottommost red node, and start from there. So this concludes the demo, and let's see if I'm doing this right. Okay. 1 second. This. Okay. Yeah. So now that the students have debugged their invariants and their grammar is working, they can actually step more confidently into the proof, knowing that their grammar works and after having validated it. So we don't want students to go into the proof trying to prove that a grammar that's not even correct works. And another thing that we find invariant predicates and invariant visualization useful for is the fact that in the proof, students can just reason about the grammar in terms of its invariance. So it makes the proof very short and simple to write.
In order to determine the effectiveness of this new tool, we ran a formative empirical study. There were 8 students that participated, and they rated statements on a Likert scale. And a quick note for the following graphs you're about to see. The reason why there are no 1 and 2 bars is because none of the students actually answered with a 1 or 2 or tended to disagree with any of the statements. So for the first set of statements, we asked them about the visualization generally. And we asked them to rate the following statements: if it helped them understand how the words are derived, if it preserved the history of the derivation, if it helped them understand how words are produced, applied non-deterministically, and if it was useful for debugging the grammars. And here, for all of the questions, the overwhelming majority of students tended to agree, answering with either a 4 or a 5. In regards to the research questions, for the first research question, whether it helps students better understand word derivation, we believe that it does due to the responses to statements 1, 2, and 3 here. Their perception was the response to question 1, and they they perceive that it does help them. And in regards to the statements 2 and 3, we think that this gives us context as to why it helps them. In regards to the second research question, whether it helps them understand non-determinism, we believe that the responses to question 3 imply that it is indeed helping them. And finally, in regards to question 4, whether it helps them in the debugging process, again, we believe the responses to the fourth statement imply that it does help them with debugging. The next set of statements were in regards to the invariant visualization. And so we asked them if they felt that the visualization of the invariance was useful, clear, useful for developing correctness proofs, and useful for debugging their grammars. And once again, for all of the questions, the overwhelming majority of students answered with either a 4 or a 5, tending to agree. In regards to the first research question, whether it helped them better understand word derivation, we believe that it does due to their responses to the first 3 statements. And here, because they responded positively, we believe that they have a strong understanding of the invariance of their grammar. And because they have a strong understanding of the invariance, that means they have an understanding of the syntactic categories, and thus understand word derivation and how is an exercise of divide and conquer. In regards to the third research question, whether it helps them develop their correctness proofs, we believe the responses to statement 3 imply that it is helping them. And in regards to the fourth research question, whether it helps them with the grammar debugging process, we believe that the responses to statement 4 also imply that it is helping them in this regard.
So for future work, for related work, one of the more notable tools for visualizing context-free grammars is JFlap. So in JFlap, students can create context-free grammars and expand the derivation tree by clicking on the non-terminal nodes. But in JFlap, the context-free grammar only fits within the visualization frame. So once you're dealing with a larger word and a larger derivation tree, it compresses into the frame, making it very difficult to read. And to our knowledge, we are the first ones to actually introduce invariant visualization in a tool like this. JFlap does not provide that option. For future work, we want to conduct more in-depth studies to answer the questions why students find the visualization and invariant visualization useful. We want to extend the work to support unrestricted grammars and extend the work to use the LL1 and LLR parsing, as well as visualize the CYK algorithm. And if you'd like to adapt our approach in your classroom, or you're just interested in any parts of it, I would encourage you to check out this book. And finally, to outline our contributions, we present a novel visualization tool for context-free grammars. It is already integrated into FSM, and it is a stepwise construction of the derivation tree with colors to indicate the current derivation step and informative messages to provide any additional context on the tree. Finally, our second contribution is a visual validation of invariance, where users can actually visualize whether their invariants hold, and we find it useful for faster debugging. The QR code is FSM on GitHub, and I invite you to check it out. Thank you for your attention. We are open to any questions.
Very nice work. I especially like the way you handled the invariant handling. I think that could be very useful. What I'm wondering about is perhaps applying this in reverse, which is to help people track down parsing errors with their own code, rather than generating grammars and debugging grammars, rather than debugging the parse errors themselves. Are your thoughts on how this could be applied there?
We've actually been looking into doing it in a more bottom-up way to achieve something like this. So it's very, very future work, but it is something that we've considered, yes.
Any more questions?
So there are a couple of phenomenons that you can sometimes notice in Likert scale-based evaluation. One of them is the I like pressing for student, and the other one is the I like pleasing my teacher student. I'm wondering if you had, when you're assessing your questions, given any consideration to asking them in a negative way. Like, I believe that I could understand better without the tool, or something like that.
So we actually have a slide prepared just in case. This was definitely a limitation of our study, the fact that the statements were phrased in a positive manner, we are planning on conducting more qualitative and quantitative studies to kind of address that. So.
But I guess when you were looking at your students' answers, did you see any students who seemed like the I like to answer for student, or did they all seem, you know, like they were varying their responses in a way that suggested they were taking it seriously?
Anecdotally, I don't think anyone is too pleased to please the teacher, at least from our batch. When it comes to kind of just pressing whatever, we've had a small enough class where anecdotally, it's been emphasized that we do appreciate kind of honesty, and it's been practiced before. We've had studies where we've gotten lower responses, so we've known, like, just experientially based on our previous studies, that that they can be objective if they like to.
Great. So maybe the standard criticism doesn't apply as much as usual.
Do we have any more questions? So if you go back to your future work slide, and you mentioned this supporting of unrestricted grammars. What do you imagine happening there? Any specific problems that might arise?
So this is already done. I'm pretty sure this is published at this point when we were making. Right. But so the problem that we have with unrestricted grammars is the fact that the derivation tree, if we're visualizing it this way, not only expands but can shrink. And we presented this last year at the student research competition here. So what we've done is we've created these special nodes that were these hexagon nodes that preserve the history of the derivation tree by showing what used to be in place of the substituted group of terminals, non-terminals. And additionally, because the tree kind of gets all over the place, we've pushed the yield all the way, or we use the special node grouping to push the yield all the way to the bottom of the tree so it's aligned, and at any point the user has kind of the idea of what the yield is and can also observe the derivation tree. Those are the main challenges. So how to design that to not make it ugly and to still preserve the history in like an effective way. So yeah. Do you have anything to add?
I will say, because we're preserving the history using those hexagon nodes, it's no longer a derivation tree, but actually a derivation graph. It just looks like a derivation tree due to the way that we're formatting it with the yield nodes all at the bottom.
Thank you. Any more questions? If not, then let's thank the speakers. Thank you.
No, it's good.
Okay, our next talk will be given by Mahinpei from Princeton University, Interactive Theorem Provers for Proof Education.
Beautiful, thank you. Hello folks, my name is Romina, and today I'll be presenting our project on interactive theorem provers for proof education, advised by Manuel Ribeiro and May Milano. And before I jump into the topic itself, I'm kind of curious, have folks here worked with interactive theorem provers before, for the most part? Okay, a large majority, perfect. And for those who haven't, I'll also give an overview of what they are, so no problems there. Okay, but just before we jump into it, so a few observations that I'm sure folks are familiar with as well. But as we know, proof techniques play a key role in the undergraduate and graduate CS curriculum in a wide range of courses, so all algorithm courses as well as formal methods, PL and whatnot. And the observation that we have at hand is that CS students tend to, one, struggle with proof-based content, and also show low engagement and also interest in the material as well. So in response to these observations, there have been a lot of investigations, so especially searches for proof technologies. These kind of range from LLMs to like intelligent tutoring systems and also different approaches. But essentially, the search for these proof-based technologies so that they can support students with learning and also increase engagement with the content as well. And specifically, there's been a lot of interest recently in using interactive theory improvers, or ITPs, as these candidate learning tools in educational contexts. And for our specific scenario, we were interested in seeing whether how well ITPs support the range of proof techniques that are covered in the CS curriculum, and how they might be improved to do so as well. But just before we jump into that, in terms of the work that we set out to do with our project, we had 3 different components. So the first was a user study, so that we could collect students' perceptions of ITPs in an educational setting. So the goal of this component was to really validate the educational promise of ITPs and add an existing data point to the existing, literature on the ITPs' use in education. And then we set out to do a case study, and here the goal was to prove 5 distinct proof exercises with 2 ITPs. So we used Lean and Rock, and the goal here was to compare the proof development process against the pen and paper process. And as a part of that, we also did a heuristic evaluation using Jacob Nielsen's usability heuristics, which is very well known to the HCI community. And the goal here was to evaluate the proof development process with these 2 ITPs and really try to identify the educational strength and limitations of ITPs and see what can be done to make them into better educational tools. So with that said, just a quick overview of interactive theory improvers for those who might not be as familiar with them. So essentially, you can think of them as an IDE for proof development, the idea being that as the user, you essentially use the proof commands that are known to the ITP. And what happens is that the current proof state gets sent to the underlying logic system, and based on whatever tactic or command you've applied, you get an updated proof state that gets sent back to the user, and it essentially displays a series of feedback and sub-goals that essentially the user has to tackle in order for the proof to be complete. And just to see a concrete example of that, so this is an example with a Lean ITP. You can kind of see in our claim over here, so you can see the variables that you have available to you, the hypothesis that's available, and the conclusion that you want to kind of make. So that's all part of your claim. And then you essentially take these, you use the proof commands known as tactics. So you apply those as the user. And essentially, as you do that, on the left side, you can kind of see the proof state, and it essentially keeps track of all the things that you have available to you. And here it kind of shows the goal. So if you go to the next step, you can kind of see how, based on the tactic that you've applied, it'll update the proof state for you. So it's essentially like gamifying that proof development process. And for most common ITPs, at least in the context of Lean and Rock, this is what the development process looks like. So with that said, in terms of like the current literature, so there has been a lot of studies advocating for the use of ITPs in this educational setting. Oftentimes, a lot of the arguments have to do with the fact that ITPs can act as active learning tools because they give this automated feedback at every step of the proof development process. And they can also, like sometimes the arguments kind of talk about the apprenticeship model of learning, where the idea is that the expert shows the student how something's supposed to be done. So that's often done in the classroom setting. And the second part is essentially that as the student, you have to essentially exhibit, it's a similar process for another task, and you have the expert give feedback. And I think oftentimes in an authentic classroom setting, we don't really have a lot of resources for that second step. And folks think that ITPs can essentially help fill that gap since the ITPs do give feedback at every step. With that said, there have also been some studies trying to integrate ITPs into educational settings, and there have been both pros and cons as a part of these studies that have come up. So oftentimes students tend to really like the immediate feedback that are given by the ITPs, so those are found very useful. But there are some issues as well, so specifically syntax of ITPs, generating a steep learning curve for students. So that's oftentimes called out in the literature. And I think specifically for us, we were interested in seeing how these issues arise in the context of different proof techniques and what can be done within that area. So with that said, I'm going to quickly jump into our user study and just walk over what we found from there. So the goal here was to really get an understanding of existing perceptions and see how ITPs do in their current state in an actual authentic classroom setting. So what we did here was essentially had students on a hands-on introductory formal methods course as part of this course, it was essentially 6 of the lectures introduced students to the ROC ITP. So we had students, as a part of those lectures, complete a series of our reproved surveys. As a part of our surveys, we had a mix of Likert scale questions where they essentially talked about their experience, where they ranked their experience with the ITP. And we also had a mix of open-ended questions as well. And as a part of the open-ended questions, we did a thematic analysis to see what issues arose and what students liked about working with ROC as a part of the course. So in terms of the surveys, so we had an initial surveys, which was administered before the first lecture to assess students' comfort with proof techniques and any prior experience that they had. We then had an experience survey, so this was administered at the end of each lecture to gather feedback on students' experiences with ROC during the in-class exercises. And then we also had our exit survey, which was given at after the very last lecture to collect reflections on the participants' overall experience. So with that said, just in terms of the student background, so we had 17 students in the course, and they were all invited to do the surveys, and 8 of them participated. So none of these students had worked with ITPs in the past, and most of them, 62.5%, felt uncomfortable with formal proof methods. So these weren't really students who you'd call experts in the setting of like formal proofs or proofs in general. And in terms of their experience, so the first finding was that ROC can actually be useful in educational settings based on the data that we got. So we actually found that 75% of students reported a positive experience with ROC. 50% found the proofs to be easier than pen and paper proofs. And 62.5% expressed interest in using this in the future. And 75% would even recommend it to their peers. So we had a lot of positive stats on it, and we were also curious to see what exactly were some of the features that students enjoyed. So we did that through our thematic analysis. So visualization features got called out a lot. This oftentimes refers to the proof state that students would see on the side. So students quite liked seeing everything worked out on their screen and seeing the current step visualized and essentially having it confirm the correctness of the whole proof. So that was one of the positives that led to those stats. We also had the feedback features, so students calling out that it was very clear when they were stuck in a proof, since at every step you do get feedback from the ITP, and they also liked how they could immediately know when something was wrong, which is not often the case when you do a pen and paper proof. And they also quite liked the systematic approach, so essentially breaking down this idea of proof development into this step-by-step process where you have to essentially think of each step independently and then try to proceed from there. But similar to the literature as well, there were some usability issues that arose in as a part of our user study as well. So specifically, 50% of students found the interface and commands difficult to learn. And when we tried to understand the root sources of those, so some issues that came up, the complex syntax was definitely one of them, with students finding it hard to use the correct syntax and thinking that they need to essentially memorize the syntax. Proof translation was another aspect. So a lot of students thinking that, okay, if they figure out the proof on paper, they couldn't quite translate it to the ROC proof right away. So there were some unable to make the parallelization there. And another issue was just the confusing error messages. So sometimes with the error messages not really pointing out what the issue at hand is, and students not really knowing how to proceed forward. So with that in mind, we essentially, through our user study, got an idea of like, okay, similar to the existing literature, there are positives and there are negatives. And through our case study, we were really interested in seeing it in the context of different proof strategies and seeing how those issues present themselves. So that said, as a part of our case study, we essentially proved 5 different proof exercises with both ROC and Lean. You can kind of see the different proof exercises that we tackled right on the screen over here, and just an example exercise at the bottom. So these exercises were from a discrete math course that was a part of an undergraduate CS curriculum. So these are the types of exercises that you'd expect your CS undergraduate student to be able to do. We were interested in seeing how that essential process would look like if you were to do it with an ITP. And before I kind of jump into one example of one of those exercises, just so that we can see what the proof problem, what the formalized proof looks like versus a pen and paper proof. I think our big takeaway here was that both ROC and Lean can support the formalization of our 5 exercises, but that Lean supports the line-by-line forward reasoning slightly better than ROC does, because ROC requires a more tactic-oriented approach. And as a part of that, Lean more closely resembles a pen and paper proof. And I'll just showcase that in a little bit with one of our exercises as well. But as a part of our case study, this is one of our main takeaways there. With that said, I'm going to now jump into one of our proof exercises. So this was the direct proof for first order logic. And here we were trying to prove that for every integer a, if 5a plus 11 is odd, then 9a plus 3 is odd as well. And this is an undergraduate student's pen and paper proof, so you can kind of see how as a part of it, you essentially just start from the hypothesis, you break it down into what it means to be odd, and it's just a bit of arithmetic and manipulation in order to show that 9a plus 3 can also be expressed in the odd format as well, and you can just call out what that factor is as a part of it. So this is the pen and paper proof that a student will essentially write, and if we try to do a similar thing with lean, so this is a lean proof, you can kind of see a lot of similarities in the sense. So again, you have your hypothesis over here and what you're trying to prove. And at the very start, you essentially you try to pull out the fact that 5a plus 11 can be written as odd using the obtain tactic. So that introduces the k factor for you right there. And then from then on, a slight difference is that at the very start, you do have to call out what the factor that you will use to prove 9a plus 3 is odd. So you have to call off that right off the bat, whereas in a pen and paper proof, that's more of a discovery process for a student. But once you have that through Lean's calc block, you can actually do that very direct arithmetic that you would do on a pen and paper proof and capture that right here as well. So there's some nice parallel to what you would do as a student on pen and paper. But now if we jump into the ROC version of it, it's slightly different because we don't have a correspondent to a calc block here. So in terms of how you would go about the proof here, so you'd first have to just introduce the hypothesis that you have at hand. And once you've gone from there, you will do a similar thing with trying to show that 5a plus 11 is indeed odd. So you introduce the k factor there. But because we don't have this calc block that supports forward reasoning, you essentially have to take each of the arithmetic steps that we had as a part of the pen and paper proof and then make them into separate assertions. So that, in some sense, doesn't really parallel what you would do on a pen and paper proof. And as a student, this oftentimes does catch students because you have to prove each step separately, which for longer proofs can be a lot more complicated for a student. And then you would apply rewrite multiple times, essentially, to then bring it to the conclusion. So in terms of ROC, there are some differences in terms of how you would go about with the pen and paper proof, whereas with Lean, it better supported that in our context for our exercises. And although I'm just showing this for exercise 2, this was a pattern that kind of emerged across all the different exercises that we were covering through our case study. Okay. So that said, the big takeaway from the case study was that obviously both ITPs are able to cover the range that we had selected for our proof exercises, with Lean better supporting the forward reasoning, so better paralleling pen and paper proofs. And then we had the heuristic evaluation part of things where we try to essentially understand the strengths and limitations and see what can be done with some of the limitations that arose when working with ITPs for these proof exercises. So with that said, I'll quickly just show the Jacob Nielsen's usability heuristics. So these are heuristics that are very often used by the HCI community when trying to evaluate new systems for different target audiences. So you can kind of see the range of heuristics that we have here. So visibility of system status, match between system and world, user control and freedom. So very varied range of them that are often used when you're trying to evaluate a system. And specifically for today's presentation, I'll focus on these 3 heuristics. So match between system and world, recognition rather than recall, and help users recover from errors, because those were the ones that we had the most interesting results for. But we do have more detailed overview in our paper of the other heuristics as well. With that said, I'm going to quickly jump into the second heuristic. So this was match between system and real world. So obviously, as we mentioned before, with Lean, so one thing to note is that it has default infix notation, which better parallels what you would see on pen and paper. It also has the support for math symbols, so for all there exists. So again, better paralleling what you would do on pen and paper. It also has this forward reasoning and computation support, which again makes things seem more similar to what a student would do on pen and paper. Now, if we were to look at ROC, it does have this default prefix notation, which for students who are directly coming from a math background, let's say, that might not hit as quickly. It also has less support for forward reasoning and computation, so you have to essentially break each step down into its own assertion. So again, causing a little bit of mismatch between the pen and paper proof and the formalized proof. And this also kind of relates to the user study theme that we had about proof translation, where students thought that there wasn't really a direct match with what they were doing on paper, what they were thinking through when they tried to make the proof work on their ITP. So that was with the match between system and real world. So for the 6th heuristic, so this was recognition rather than recall. So something to note is that both of these ITPs do provide search support. So once you know what tactic you want to work with, you can essentially they provide search functions that help you look through the documentation of those specific tactics. But as a user, you essentially need to remember the proper application of a tactic and how you're supposed to use it. And this relates to our user study theme of complex syntax. So it's students thinking they have to memorize things, essentially, to be able to work with these ITPs. And that was something that came up as we were working through our case study and doing the heuristic evaluation as well. And I think on our end, we thought that maybe providing more concrete examples of tactic applications will better support example-driven learning. So you can kind of imagine this almost as a hover over feature, where as a part of hovering over the particular tactic, the student can see examples, and then they can try to essentially mimic that into the particular scenario that they're dealing with. So then for the ninth heuristic that we're going to talk about today, so this was help users recover from errors. So oftentimes the errors from these ITPs, and this was something that we noticed in our case study as well, they tend to be too technical and not very actionable. And oftentimes they tend to be very low level as well and not really directly hitting what the target issue is at hand. So for this particular example here, so you can see an error message from Lean, and you can kind of see the corresponding proof that we have here as well. And the issue at hand, you see the red squiggle, and the real issue at hand is just that we have this invalid token, the hyphen. That's the only issue that we have. But the error message itself kind of talks about the rewrite tactic not being able to progress. So oftentimes the error messages don't really point you in the correct direction, and that can be very frustrating to students who are mostly using these tools for a proof development process rather than learning to work with the tool itself. And this was something that we noticed with Rock as well. So this wasn't just a Lean issue, but definitely came up with both ITPs. Okay, with that said, some of the big takeaways that we had. So obviously ITPs do hold considerable promise as tools for proof development. Some themes that came up, so they can facilitate the learning of formalization, and they in some sense gamify the proof development process, which can be a bit more fun for students to kind of go through. And they also provide that instant assistance that oftentimes is very hard for us to provide in a real classroom setting just because of the limited resources that we have at hand. But at the same time, their usability will need to improve before we can really repurpose these tools as candidate learning tools for a larger population. Specifically, so in terms of future work, there can be a lot done to essentially make these tools into better educational tools. And some of those we kind of directly called out as a part of the heuristic evaluation. So one, trying to improve the error messages to be more actionable and personalized. Two, trying to strengthen the support for example-driven learning. So essentially trying to make the tactics a little bit easier to work with. And also three, to further help with the learning curve, we thought it would be very interesting to look into automated assistance, so perhaps through LLM integration or AI integration of some sort. Other things to also keep in mind in terms of future work, obviously there's a lot of limitations as a part of our work since it was limited in scope, but exploring perceptions ITPs with a broader population, we were kind of restricting the size of our sample there. Also exploring a broader range of ITPs, so in our work we specifically focused on two, so Lean and Rock, and there's a much wider range to look at there. And we were also very interested in exploring ITP formalization of a broader range of proof techniques, because we were kind of restricted to 5 techniques in our work. And I know there's been a lot of work in UK actually in terms of trying to formalize the mathematics undergraduate curriculum. And we thought it would be pretty interesting to try and parallel that work and do a similar thing for the CS curriculum as well. So to try to cover the broad range and see what issues arise as a part of using ITPs for that process. But with that said, thank you for listening. So that is the end, and I'd be happy to answer any questions. I can hear you, but I don't think the mic is working.
Oh, there it goes. All right. Thank you for the talk. It was very interesting. I'm wondering if you had any observations or noticed anything about students over-relying on an ITP. So for example, the ITP will put goals in front of them and tell them what the next step that they need to prove is. Did you notice any students that hurting their ability to write a pen and paper proof where they maybe over-rely on the ITP putting that next step in front of them?
So not in particular in our context, because for the course that we were working with actually, so the 6 lectures that used Rock were actually at the end of the course. So up to that point, students were actually doing everything on pen and paper. So the scenario that we ran into a lot in our case was that students would actually try to logically think through it on pen and paper first, before trying to translate it to Rock. So we didn't run into that issue as much, but it'd be interesting to see if that would potentially arise if we had flipped the ordering of the course material.
Yeah, thanks.
Great talk. It's really nice to see someone taking the annoyingly hard task of trying to justify kind of something that I think the field intuitively really wants to have happen, and a number of us have tried to do in various capacities. Rob's question kind of got to my first thing about transfer in some sense, right? Because I think what I've noticed in my own classroom is the transfer problem from ITPs to paper proofs a really real phenomenon, and something you can't kind of overestimate. I'm kind of curious if you saw another phenomenon in your class, in your data gathering that we saw at Penn in our graduate class. I think a lot of people see in their graduate classes kind of the phenomenon of the bimodal split with ITPs, where basically the functional programming nerds get it and then everyone else hates it. And yeah, I find that has been, overcoming that's been very difficult for classroom deployment. So.
Yeah, so that's a very interesting question, because I think before like looking at the data, we were also kind of expecting a similar trend. But interestingly enough, because all the students that at least participated in our survey, none of them were really comfortable with formal methods, and majority of them had not worked with ITPs in the past. So out of that population, we still got a lot of positive signals in terms of like using these ITPs for that educational context of things. But I think going into it as well, we were kind of expecting a similar pattern of like people who weren't really as into like formal methods or these tools to begin with wouldn't really enjoy them. But from our data, at least, again, limited in scope, but we didn't really get that hypothesis done.
Just dawned on me real quick, in your deployment of it, did you, in your introduction to ITPs, did you use as a test bed for introducing functional programming? Because I think that actually might be a distinction in curriculum. So if you avoid that, then maybe you avoid that stigma from arising.
Yeah, so I think in our context with the course itself, it was basically targeted as a formal methods course. So we were covering like a majority of like topics from lambda calculus to like core logic. So it wasn't really like, framed as like a functional programming course, if that makes any sense, more so as more of like a formal methods course. So maybe that could potentially explain some of those trends.
Functional programming sucks. In a similar way, you need to like plan out and design what your program is going to be before you make it. I imagine you need to do the same with a proof. Have you put any effort towards how you would systematically develop a proof in an ITP?
So I think like as a part of like our, at least when we were doing the case study, I think that oftentimes the approach that we took was to try and to like take the pen and paper proof and try to like translate that. So I think for us it was a matter of like going from the pen and paper proof, trying to formalize that. So we didn't try to formalize the approach that we took. So I think as a part of our work, we didn't try to like, I guess, make a framework of what that approach looks like. But I think as a part of the experience itself, oftentimes our approach was to just take the pen and paper approach and try to see what the corresponding formalized way would look.
Last question now, but maybe the next speaker could already start setting up so that we are.
Great talk. I'm sort of coming from like an education background, and I don't have too much PL or math, I guess, formally. But I know there was some discussion about a previous talk went over like a educational, like a subset of Pirate. Mm-hmm. Have you thought about if that would be like a good solution maybe to some of the experiences that you were seeing with students, their issues? Like, is there a subset of this rock or lean that you think would be a good, like, minimal set of features that would be good educational in this setting?
Yeah, I think definitely like there's a lot of, I guess like if you were to like separate some of the features, I think if we were to like integrate those into like more educational based tools, that definitely is one way to go about it. I think right now the approach that a lot of folks are focusing on is in terms of like repurposing the existing tools as things that can be used in an educational context. But I think it'd be very interesting to try and take it from the separate approach of like, okay, these are the features of these tools that work great in an educational context. So let's take them into like another educational tool and see how that goes. So So definitely as part of future work, that'd be very interesting to look into.
Yeah, thank you very much. Thank you. Next talk will be given by Florian Ziller on a serious game to teach writing, reading, and debugging programs.
So, hi everyone. We take a step away from formal methods and proving and go into a serious game to teach not just writing programs, but also comprehending and debugging programs. And so first of all, you might ask yourself the question, why do we do what we do? And here's already a glimpse at how the final product then looks. So first of all, we do this to support, investigate, and motivate to teaching the full programming process in and of itself. So it's not just the creation of programs or learning its syntax or its semantics alone. It's about learning to read programs that are written by others and to comprehend what they're doing. Just earlier in the Splashy track, we also learned about LLMs generating code, and we have to critically think about what the code is then actually doing. And then again, we think it's very important to support this endeavor. All in all, the game that we created, the serious game, is focused on programming novices. And so far we started it to test it out and teach it with novices as young as the age of 12 in German schools. And is designed for an introductory course of roughly 3 hours. You can play with it much longer, but all of the experiments we've done so far were constrained to a 3-hour spectrum where the students usually had no idea of what programming is before, and afterwards hopefully had some idea of what the concept is about. And the game itself, due to the time constraint, focuses mostly on procedural concepts, but there's also object-oriented concepts in the back, but usually we weren't able to get to them in 3 hours. And all of this, as you might have heard so far, is work in progress. So this is one of the non-archival papers, so if you have any ideas about what we're doing and you like the endeavor or something, feel free to come up to me and we can start a discussion, so this would be really nice. So to make a quick jump to what the game looks like and to give you a brief overview, in general, we have this playing field here where there's a penguin. We can see it. Use a laser pointer, we can see it right here. This is the main character, and then there is a challenge for the students to solve, which of course gets incrementally harder over the levels and teaches them to use various programming concepts. For example, for this level here, they have to write their own program to control the penguin so that it in some way reaches the igloo that is located in the lower right. And the program could look something like this. And there you see a couple of aspects of the language which are already really advanced. So this is, of course, not the first programs that the students must write, but you can define your own functions. There is an optional typing system. There are loops in various formats. And there are ways that the students can control the penguin in and of itself on the game field to reach and achieve the actual goal. So how did all of this come to pass? So just to give you a quick history of how we arrived at that point. In general, the game was conceived at the university as a way to fill in for a public relations event where we needed something. And so we conceived the idea on March 17th, implemented the game basically in 2 nights, and then, if the animations work, yes, on April 1st we had effectively the first application of this event where we tested it out with a couple of young children in this scenario for the Girls' Day, where in Germany there's an event for girls to try out computer science, electrical engineering, and other studies that are at least stereotypically not as common for girls and women. And then the game went on, and on any other PR event we tested out the game even further. We extended it, we extended the functionality, and over the months and over the years we reached the prototype that we currently have, that we've studied with a couple of children and younger students, and arrived at a feature set that we feel comfortable with to really teach them and show them how the programming concept actually works. So how is the game constructed? What are its features? In general, the whole game runs as a web application. It's also deployed. There will be a QR code in the back where you can test it out if you like. It runs with TypeScript and React, uses Pixie.js to effectively render the scene, and for the language itself, as I mentioned earlier, we're using a custom domain-specific language. We use a combination of the Monaca editor, which is the editor behind Visual Studio Code, and the Langium language framework, which is effectively what came from Eclipse and Xtext and worked quite well for us to implement the language. And with all of these capabilities, and with our custom DSL, we provided a huge set of features. As I said earlier, it focuses on procedural concepts, but also provides object-oriented principles. It provides things like autocompletion, syntax highlighting, type checking, so on and so forth. It relies on a coroutine implementation of the interpreter, because one of the most important things I haven't told you as far, everything in the game that you see and that you can interact with is actually written in the DSL as well. So we effectively force the students to interact with the language by, if there's water, if there's a fish on the ground, anything that the penguin can interact with in one way or another, the logic, how the student can interact with the penguin or like other penguins that might move over the field as well, is all implemented within the DSL as well. And there's a sophisticated coroutine interpreter that is effectively interleaving all of these semantics and showing the students what's going on. There are many more of these features. We have hints. There's a interrogative time-traveling debugger that they can use to find out what's actually happening. There are various learning paths for basic procedural and even imperative concepts. And there are integrated quizzes because, of course, we wanted to use all of this to find out whether they actually learn something. And so we are effectively recording everything the students do when they're interacting with the environment. And there are extensive docs, even though if you want to check them out, we did this at German schools, so the documentation that's like used as a reference is mostly in German, but we're working on translating that as well. So I already told you that most of the elements that the students can interact with are already written. Well, all of them are also written in the same domain-specific language. What does this mean? For example, here we have a very simple level. It's one of the earlier levels. The penguin, again, has to reach the igloo, very simple, but now there's another penguin on the game field. And if they actually inspect the implementation of this penguin, that they can see that it will move 3 times into its looking direction, so movement is defined locally. And if we are taking the naive approach of ignoring that penguin and just trying to move 4 steps, we effectively encounter the problem that when we move a step, the other penguin moves a step, it's effectively in the way. And now, depending on whether the penguins can push each other, we have a problem that we can no longer reach the igloo. So one of the solutions that now the students have to come up exploratively, and again, if you know programming, that's very easy. You can in any matter delay the movement of the penguin to leave the other penguin to move past and then get through. So what we can, for example, do is we can insert a wait instruction, which then causes the penguin to do nothing for 1 step. And what we now have is that, of course, the penguin can pass because the other penguin moves 1 step forward, and we effectively reach the goal. If I have time, there will be a live demo of this later as well. So with all of these semantics, we of course have other penguins that can be moved, but as I said you earlier, everything is effectively described in the language. So if we have a bigger field, as I've shown you earlier, you can inspect the water, and again, the water will be implemented within this DSL as well, and again, you can see some more sophisticated features. And on the other hand, for example, the fish that's lying on the ground is implemented as well in that DSL. And then again, if the students want to understand what they can do with these elements, because there will be no direct explanations of what they're actually supposed to do, they have to read through the code and understand what it actually does. And you can see here one of the more specifics of the domain-specific language, because of course there are conditionals, there are loops, there are functions, but one of the 2 important things is that actually every entity can have one special thing that it is able to do that we hide behind an ACT implementation to make it easier for the students to read. Like, for example, other penguins can lay down stones as markers, or can wave hello, or they can trade fishes, or whatever. And on the other hand, we have world references. So with the world keyword, effectively, or with the world object, students can access every element that's on the playing field to effectively interact to check whether the element before them is the other penguin that they were inspecting. And so far, I've only shown you the game in a very simplified state, because I only showed you the game board. How does it actually look when you open it up in the browser? It looks roughly like this. So on the left-hand side, you have the code editor, where you can write your implementation in the domain-specific language. In the lower left, you have some logging information, which effectively presents you with an information about the current game state. Then on the lower right-hand side, there is some intro hook, again written in German, so that's not important as of now, but it gives a brief primer of what is supposed to be achieved in this level. And in the upper center, slightly left, you have the game controls, which you can then use to run the simulation of your current code. And when the simulation is in play, yes, when we start the simulation, you will effectively see a stepwise play of how the codes intertwine, and you can see the current state of the actual execution. And you can also stop it, and you can call for the debugger that I was calling to earlier, where you effectively are able to step forward, step backward through the execution and see why the code didn't perform as you might have expected it to. And In the back, we have, of course, these learning paths. So I've shown you some selective levels, but there are actually a couple of levels. So far, we've implemented 42, because, of course, we have implemented 42. And they are separated into these learning paths above. So we start with normal imperative concepts. We then extend them with conditionals, add loops, and in the end, we teach them like procedural and functions. And again, we also have object-oriented levels, but we don't get to them in the 3-hour context. Then we have our levels, and each level is effectively indicated either by just whether the student was able to complete the level, or some of these levels also implement score mechanics, where they, for example, have to use less instructions, or where there are multiple obvious solutions to the level, and they can figure out some more clever ways to solve it actually. And if we're now switching to the quiz implementation, where we're tracking what the students are actually doing, we add these darker teal-blue bars, which are effectively quizzes, which can be used to check whether the students have actually understood what they're doing. They're questioned on these things, and they're also recorded depending on like what they agreed to, what code they write, when they press the play button, and so on and so forth. So what do these quizzes look like? Again, I've brought some examples here on the slide, and we can do a live demo later. For example, this is one of the earlier quizzes, where we again reiterate on the weighting mechanic. The students are shown a specific playfield state. They are shown the codes of several entities. In this case, again, we just have 2. And then they're questioned. They're, of course, closed answers. There are also quizzes with open answers, what the final game state will be, forcing them to not having any simulation at hand, effectively do the simulation in their head, and again, find out what the final game state will be and what the game is supposed to do. And there are, of course, other questions which serve a more general purpose, where we try to grasp their understanding of whether they have really understood what the concept of, for example, looping in the scenario really means, where we ask them, for example, to either come up with predefined or their own scenarios where they would like think looping structures and looping instructions could help, either in a programming context or in a general real-world context, to see how their application generalizes. Again, when we are like recording these students, we record a lot of information. This is a very simplified and summarized view, where for every level, we record like every button press they do. We're kind of like Amazon in that regard, and have a clickstream-like tracking of whatever they intend to achieve. And we track their editor state, which operations they do, when they do these operations. Of course, with the timestamps, we can also intertwine these with students who are like brute forcing their solutions by just typing things in, then pressing play, watching whether it works, or students who take a much more like systematic approach, where they first think, then they try a solution, and then it takes some time until they press the play button. And also we record the information for the quizzes. And of course, alongside of these things, we also have automated analysis tools to like evaluate the results of these things, where we can generate like time graphs, so we can see where the student produced which code. We can also identify how they layouted these things, whether they were like stumbled by syntactical errors in the language, and whether they use debugging elements, in which scenarios they use the debugging elements, and then we can evaluate these things. So again, I said so far, this is all work in progress. So we so far mainly had like things we call preliminary observations, because of course we had children that tried to explore the game, but all of them were in different scenarios. They were children of different age groups. So far we had 56 participants who agreed to data sharing of the ages 12 to 17, but we wouldn't call this a systematic study, because that's what we want to do next with the preliminary results that we have, because again, they were in different scenarios. Some of them already knew programming, and we only used them as like a main pre-study guiding way of refining the game's semantics. But again, most of them had little to no prior experience with actual coding, programming, or any of the related terms. So what were our key observations so far? We first of all found that they were all highly motivated. Again, this might be a bias of them knowing that we have a game here that we want to explore, and all of the instructors were pretty motivated, and especially with younger children, that tends to like mirror on their emotional state. But what we really found enjoyable and quite surprising is how they engaged in uninitiated, self-started collaborations. So they formed little groups solving harder levels together, or when one of the children was stuck, they helped this child or this other kid or student to solve the specific problem, and even started to explain them how they understood the respective programming concepts. So without us initiating these things, when someone wasn't able to understand what a loop is, someone was happy to help and try to explain them how they understood what the looping structure is actually supposed to do. Furthermore, we found that the debugging was perceived useful, but only after they were shown that debugging can help in a specific individual problem. So far, none of the students started to use the debugger from themselves in these scenarios and try to find out what is wrong. It was always one of like the instructors of us walking around, seeing that the student struggles and then telling them, hey, have you tried the debugger? And then they started using the debugger, and then they actually found the problem rather quickly and then said they perceived it as useful, and then they started to use it on their own, but it was only after these scenarios where they were confronted with a problem where they actually started using it by themselves. Furthermore, we had active visualization, so I hinted at that earlier, but in the game everything is defined by the current perspective of the penguin. So if you want to turn right, you actually have to turn around the penguin first, which then caused like students on their rotary chairs to try to simulate the game in their mind and rotate with the chair to try to find the current orientation and location of the penguin in a specific state of the program. And after the session, most of them perceived a clear improvement, but then again, we don't want to claim that they actually clearly improved, because that was more of a self-assessment and we can like infer from how they answered the quizzes, but 3 hours and then a short questionnaire aren't enough to really make definite statements of that so far. So what do we want to achieve with the real big whatever evaluation? One, of course, see the change in motivation. So one thing we want to achieve is that people get motivated with computer science, with programming, but also realizing that it's not just coding and sitting in front of a machine and typing in code, it's also reading code, thinking about simulations, so on and so forth. We've talked about this the whole day. Then we want to analyze their problem-solving approaches. As I said earlier, the preliminary data that we have clearly shows that some of them are really systematic in their way. They try to break down the problem. We can see the code that they write way before they actually even execute the program. And on the other hand, we have students which like just type in a couple of commands, press play, see that it doesn't work, try to reiterate on the code, and kind of work like an LLM with various iterations on self-improvements until the level is solved. Furthermore, we want to see how like debugging and comprehension ability actually interplay together. Again, we already noticed one of the effects that they don't seem to find an intuitive way of start to using it themselves, but maybe we can find more clearer reasons about how we can incentivize these things. And then again, of course, we want to get more information about the actual learning effect that we can achieve in 3 hours, especially if they've never programmed before. But again, I mean, we have a lot of plans. There are also some open questions. We want to support and compare with other paradigms and interactive tutorial elements, because right now the whole system still relies on some instructors being present, for example, to point them out that, hey, there is a debugger, but we would like it much more if there would be an implemented, like integrated way who realizes, hey, the student is struggling, have you tried the debugger? And then see whether this helps. We also want to involve concurrency, because again, we have all of these entities already interplaying with each other. Currently, there's a deterministic way where effectively they're sequentially interweaved, and so the student can always know when which entity is about to move, and yeah, we want to break that up and make some more concurrent events happening. Of course, we want to compare it with other serious games, because there are plenty. And last but not least, we of course want to compare it with the, as it was called this morning, magical text understanding device. So like with how LLMs are able to teach programming and whether there are differences, especially regarding the critical comprehension. And with that, I'm basically at the end. So if you want to check out the game, there's a QR code on the left. It should work on mobile, even though we haven't optimized it to work on mobile. And we can either go directly to the questions, or if you like, I can show you a live demo. I'm open to both. Okay, who's for questions? Who's for the live demo? Okay, then by pure means of democratic reasoning, live demo wins. So this, maybe I mirror the displays again, so that I see what you see. All right. So this is the main game. This is where the QR code should have led you to. We can press on start. We can see the level menu. We can start with the first level, because I think that will be very challenging for all of us, where we're effectively introduced by moving the penguin to the igloo on the right. And the only thing the students know so far is that there is this pengu object like that they can write out in the code to do some work. And if they do so, we can also see like the auto-completion at play. So most of the students rather intuitively started to use the autocomplete. Maybe they know it from other editors. And then you can effectively re-trigger the autocomplete and then find other methods that you can use with the Penguin. And just by pure exploration, you maybe find at one point that there's move. And the only other thing we told them that they can start the simulation with the play button. So if you now press play, you can see the Penguin moving one step. And yeah, that's basically the simulation we've seen so far. And you can go one step back, kind of laggy, and you can again one step forward again. And so you can like debug now this one-step operation, which isn't as helpful. Then of course we can take this statement and repeat it a couple of times. And now, luckily, I know how to solve this level. We can make the Penguin reach the igloo and proceed to the next level. And there, again, we have the problem that now we can no longer go straight, so they have to re-explore what other options there are and effectively get a grasp on now very, very basic imperative concepts, because they first have to learn how to move the Penguin, and then this incrementally gets more and more difficult. Okay? If I now quickly switch to the quiz mode, which we of course don't tell the students how to do, because then they can leave it as well. And now we added the questionnaires, which again are in German. But if we're now playing through games, like we can, for example, retry the level we just tried, and I speed this up just a little. And we solve it again. And now we think that the students played through all of the 3 hours and had a lot of fun and learned a lot of things and everything went great. And maybe we can even try to look into a questionnaire, which again is in German. But then here are the challenges that they can answer, that they can solve, where they have to answer these questions. We can click on a random button and then say we answered the whole questionnaire, which one's great. Then after the quiz ended, we effectively get this beautiful, okay, now with black, this is really unreadable. 1 second. We effectively get this beautiful JSON document, which effectively contains all of the information I've shown you earlier, where we then can see, for example, here, when I press the play button, whether I've resetted the level, what the code looked like when I pressed the play button here. This is the solution that I wrote. And then again, of course, if I now would have taken more approaches and coded more things, there would be much more here to see and then to analyze and evaluate. So yeah, this was a very short live demo. I can also like dip into one of the later levels so that just that you can see what's possible there. Which one do we take? So for example, this is now one of the bigger levels that comes later in the game, where you have many more penguins, where you have to understand what they're doing, where they will move to then again in this level reach the igloo. But then there are many other languages where we have many other levels where you, for example, have to move boxes to allow another penguin to cross path, where there are buttons that then interplay with spikes that then cause a path to become viable or non-viable, where there are ice cubes on the water that actually move non-deterministically, and then you have to effectively like use conditions and everything to wait until the ice block is in front of you, then move one field further, and so on and so on. And this is effectively the level structure that we've prepared, and I think with that we are ready for the questions.
We have 1 minute, 30 seconds.
So it's interesting your observation about the hesitation to use the debugger, because even normal programmers have the same problem. You know, we all reach out to printf. And I have 2 questions. One, were there observations that you were able to make about the students and what might be causing that hesitation in them? The other question is, you said they did eventually use it when it was prompted. Now, was that they had to be prompted on a problem that they were specifically having? Could it have been demoed? Is there a way we could have engineered that? And it sounds like once they prompted it once, they didn't have to be prompted again. Is that correct? Okay.
Yes. I mean, some of them didn't use the debugger even after being prompted, but most of them then did. So it's a difficult question. So in general, we found that most of the students just like prefer the classic software engineering system out print line approach, even though we haven't shown them that you can actually print to the console, so hey. But they could just explore the game state because there was no like permanent failure, so they're like, and we don't want to implement that because that would probably hurt their motivation. But in general, that caused them to just like try out various implementations, and then they were happy. And yes, it was like, if we just showed them the debugger even at the start, because we tried it once at the start with like 20 participants, and I just showed them that you can move back and forward, and that may help you to understand more complicated levels, still no one used them. So it was mostly when they were stuck at a level, and the hint was mostly a, hey, have you tried to use the debugger? You can step forward and you can step backward. And then they started to explore with it, and usually they found it useful, and then they started using it.
When you demoed it at the start did you demo it in such a way that it was like, oh no, I have a problem, therefore this is my solution, rather than just here's the functionality?
Yes, but there was the severe bias that it was a very simple problem, because otherwise I would have needed much more complicated constructs that they then didn't know. So there's still an open challenge how to like make the problem complicated enough that they maybe perceive it useful without using loops, functions, and 10 other penguins.
Okay, any generalizable insights that might help us get over debugger hesitation in other developers?
So far, no, but maybe after we did the real study.
Okay.
But like, we have real hopes in like having an automated system that when it like perceives users being stuck, then hinting them at, hey, have you tried using the debugger? But we haven't tried that so far, so I can't report on its effectiveness.
I guess we have to continue to the next
Okay,
talk.
okay.
Thank you very much. So the last talk of the session will be given remotely, and this is a pre-recording. So personalization of programming education and NLP-based bidimensional classification of programming exercises.
Good day, everyone. Today I'm presenting our work, Personalization of Programming Education and NLP-based bidimensional classification of programming exercises. This is a joint work with my colleagues Gijs Walravens, Mazja Sarai, Linia Ochoa Venegas, and Mark van den Brand at Eindhoven University of Technology. So let me start by setting up the problem we're addressing. So programming education is experiencing a massive global growth. It's now recognized as a core literacy, similar to mathematics or science. But this creates a significant challenge. We're seeing mass classes with hundreds of students per course. And the problem is that the teaching methods we know best, personalized learning and active learning, are becoming incredibly time-consuming at this scale. So when you have hundreds of students, you simply can't provide individual feedback and tailored exercises the way you could with smaller groups. So this is driving the need for automated exercise systems that can maintain educational quality while reducing the workload. But these systems, they require a systematic understanding of existing exercises. Namely, what kind of exercises do these systems need to be working with? So what does the current landscape of exercise classification look like? First, there's a fundamental scaling problem. As mentioned before, manual labeling of exercises becomes increasingly impractical as the volume of content and learners grow. Looking at existing approaches, they tend to focus on single dimensions. So for topic classification, most work relies on curricula and textbooks, but the main problem is these aren't data-driven. So they assume predefined frameworks rather than discovering topics from the exercises themselves. Then for difficulty classification, we see three main limitations. Some approaches use extensive performance metrics, but these require a large data set. These large data sets that aren't available for new exercises. And others rely on expert judgment, as this shows systematic bias. And mathematical approaches tend to produce overly broad categories that don't distinguish well between similar exercises. So what's needed is a systematic, automated approach that handles both dimensions, so topic and difficulty. And that's the gap we are addressing. So how do we address these classifications? We looked at domain-specific lexicons, which have shown remarkable success in other fields. But the problem is programming education lacks this dedicated lexicon. At the same time, there's been recent work using large language models like GPT-4 for exercise generation. While promising, these approaches face significant barriers. They have high computational costs, and more importantly, they lack interpretability. So these black box models make it difficult to understand or trust how exercises are being classified or generated, which is a real problem for educational quality assurance. Our approach positions itself as a resource-efficient and transparent alternative using lexicon-based NLP methods. Then this leads us to our two research questions. First, to what extent can machine learning and NLP methods effectively identify and classify educational topics in programming exercises? And secondly, to what extent can ML and NLP methods effectively predict difficulty levels of exercises? So these questions, they guide our investigation into whether automated classification can assist educators in understanding and organizing their exercise content at a scale. Our approach combines three components. So we start with exercise descriptions and a Python-specific lexicon. These feed into NLP methods that perform two tasks. So topic classification and difficulty prediction. And this bidimensional analysis then provides a comprehensive understanding for each exercise. And the idea is straightforward. If we can systematically understand what characterizes existing exercises, so both their topic and their difficulty, we can then use that understanding to support the creation of new and appropriate exercises for all kinds of different learning contexts. On to our methods. Our dataset consists of 106 Python programming exercises from 3 introductory programming courses at the TU Eindhoven. So each exercise is formatted as a Jupyter notebook with a description and a reference solution. For difficulty prediction, we have student performance data from a subset of exercises, specifically 32 exercises across 5 different sets, which in the end gives us a total of 5,522 data points. And for topic classification validation, we manually labeled exercises using established CS1 topics. 2 raters independently performed this labeling and then met to reach consensus on all exercises. This provides ground truth for evaluating our automatic topic modeling approach. We then construct the Python specific lexicon, which is a core component of our approach. So we built this lexicon systematically from 4 sources. So the first one is Python reserved words like return and lambda from the keyword module. Then built-in functions like print and range from the built-ins module. Third, data types like Boolean and integer from the official Python documentation. And lastly, general programming terms like variable and element from a Python educational textbook. So to maximize our filtering capability, we expanded the lexicon to include all variations of each word. So to be precise, with this we mean all the inflections of their lemmas. So for example, instead of only including integer, we also include integers. And for example, for the word set, we include it as a verb, a noun, and an adjective. So this expansion means we can match more instances when filtering the descriptions without losing semantic information. Then for topic classification, we use per topic, which recent research shows outperforms traditional methods like LDA and top2vec. The pipeline works as follows. First, we filter exercise descriptions using our lexicon to focus on programming relevant terms. Then we generate BERT embeddings, and these capture contextual relationships between the words. And here a key choice in our method is that we keep the stop words during the embedding to preserve the context, but then remove them before the next step to avoid noise in the topic representations. So next, we reduce dimensionality, and then we apply clustering to automatically determine the exercise groups. And finally, we identify representative words for each topic. Then we evaluate this in an ablation study across 100 iterations, comparing our full approach against variants without lexicon filtering, and also an approach without stopwords during the embedding. Then to assess this, we use 5 different metrics. The ARI score for alignment with our manual topic labels, the NPMI and CV for the coherence of the topics, and lastly, the topic count and the outliers for the stability of the resulting topics. And for difficulty prediction, we use a supervised learning approach. We process exercise descriptions using TF-IDF factorization combined with our lexicon. So our difficulty metric is the average student score per exercise. This is an established approach in the literature, but we acknowledge the ongoing discussion surrounding the reliability of the difficulty level metric. Then we evaluate 5 supervised machine learning models, linear regression, ridge regression for regularization, lasso for feature selection, random forest to capture non-linear relationships, and SVM for handling complex patterns in high-dimensional space. Similar to topic modeling, we run 100 iterations, comparing our lexicon-based approach against the baseline without lexicon filtering. And we evaluate using the root mean squared error and the R-squared to assess both precision and reliability. Then onto the results. So what did the lexicon construction produce? So we ended up with 318 unique terms, which expanded to 715 variations. Then more importantly, we can look at the impact it had on the feature space. So for TF-IDF factorization, we went from around 2,000 features down to 246 features, which is an 88% reduction. And then for BERT embeddings, we reduced from a bit less than 2K to 715 features, which is still a reduction of 62%. Then what did this lexicon achieve in combination with the BERT topic at topic modeling? So let's start with the classification accuracy, which is measured by the adjusted RAND index. So again, in the middle, we have our approach, and on the left, we have the baseline without our lexicon filtering, and on the right, the baseline that doesn't use stopwords in the embedding phase, but uses the lexicon. So here we see a clear improvement. The lexicon-based approaches achieve an ARI of 0.33 compared to the baseline's 0.21, which is a statistically significant difference. And furthermore, we see that lexicon methods also show tighter boxes, so they reduce the variability across the 100 iterations, which means a more consistent performance. Then moving to topic coherence, the results are a bit more mixed. So looking at the NPMI scores, we see that the approach without stopwords performs best, achieving a positive score of around 0.02. And the lexicon approach with stopwords and the baseline both score below 0. This indicates a worse than chance performance. And also notice that the baseline has a much wider box on the NPMI score, indicating even more inconsistent coherence. Then for the CV coherence metric, it tells a similar story, although a bit better performance. So again, removing the stopwords gives the best coherence score at about 0.6, and the baseline and lexicon with stopwords show intermediate performance around 0.45 or 0.48. So overall, all methods struggle with coherence, but the no stopwords variant performs best, and it does so consistently better than the baseline. Then for clustering stability, we look at topic count consistency on the left, the lexicon approach with stopwords, so our suggested method, the middle one, produces the most stable number of topics with a tight distribution around 8 topics. The baseline varies wildly, anywhere from 2 to 11 topics across different runs. And so this stability is important because it means that the lexicon approach reliably identifies a consistent structure in the data. And lastly, on the right, outlier count shows how well the exercises fit into topics. So both lexicon approaches produce substantially fewer outliers, so around 8 to 10 exercises on average, compared to the baseline's 20 outliers. So fewer outliers means better defined topics, where most exercises are belonging to a specific cluster. Then moving to difficulty prediction results, we see a much more varied performance across our models. So at the top, linear and rich regression with lexicon filtering perform the best, achieving an R squared of around 0.37 and 0.41, with a root mean squared error of 0.05. So for these models, the lexicon method significantly improved the performance across iterations. Then for random forest, it showed poor performance with an R squared of about 0.24. And the lexicon still provides improvements here, but a more modest one. Then lastly, the lasso regression and SVM perform at the below chance level, so R squared less than 0. And notably here, also the lexicon provided no benefit in their performance. However, we also need to acknowledge some significant limitations. All models show a high variability across the 100 iterations. And even more critically, our best root mean squared error of 0.05 spans nearly the entire interquartile range of student scores. So this indicates that while the lexicon consistently improves performance, the practical utility remains a bit limited. So then what do these findings mean for educators? First, the Python-specific lexicon itself is a contribution. So it provides a shared vocabulary for representing fundamental programming topics. So this can support the design and evaluation of educational materials and help standardize topic coverage across programming courses. Though we acknowledge it needs some further development and validation. Second, looking at our classification results, the lexicon combined with NLP methods effectively support topic-based exercise classification. This works well. However, the difficulty prediction is a whole different story. It still requires better metrics and more robust methods. Third and final, and maybe most important for practical applications, is our framework, which provides transparent and interpretable classifications, so educators can understand and trust how topics are identified. Comparing this to LLM-based approaches like GPT-4, which are black boxes with high computational costs. And from a research perspective, there are several directions forward. First, again, the lexicon itself, it needs a bit more work. So we need a mixed method approach to evaluate and extend it, both quantitatively and qualitatively. Then second, the framework expansion. So our bidimensional approach is just a starting point. Future work could explore additional dimensions like Bloom's taxonomy, cognitive complexity, and for example, learning outcome alignment. And critically, difficulty measurements remain an open research topic. So our results contribute to the ongoing discussion about how to use performance data to estimate the exercise difficulty. And third, this work is also an invitation to keep exploring the resource efficient solutions rather than defaulting to computationally expensive LLMs. And then finally, this classification framework serves as a building block for adaptive learning systems and intelligent tutoring. So systems that can tailor content to individual learners based on systematic understanding of the exercise characteristics. So let me wrap up by directly answering our two research questions. So first, can machine learning and NLP methods effectively identify and classify educational topics? Yes, our lexicon-based approaches significantly outperform the baseline with clear improvements in accuracy and stability. And this provides a transparent alternative to resource-intensive LLM approaches? And second, can these methods predict difficulty levels effectively? Yeah, here we see limited success. So the lexicon consistently improves performance across most models, but practical utility remains really constrained. So better difficulty metrics and expanded data sets are needed. Then our main contribution, first, a Python-specific lexicon for programming exercise classification, and second, a bidimensional framework for automated exercise generation systems. That wraps it up. Thank you for your attention.
So I'm understanding is that we have authors online, so we can ask questions and they will be able to answer.
Hello, everyone.
Yeah. Yeah. Any questions?
Yeah, my question is regarding possible application in the area of teaching large classes. When you are looking at classification of answers, students answering questions, something similar comes up where you may want to classify answers in according to their relevance to the topic, according to their quality, but also you may want to classify answers with respect to you might want to group answers into baskets so that you can grade the answers and comment and give feedback in a more effective way in very large classes. So would your approach be applicable to that scenario?
Thanks for your question. Are you hearing me?
Yes, we can hear it. Yeah.
That's a very interesting question. So I think that the method that we developed could be, let's say, migrated and applied for the answers part. In particularly when you were like formulating the question, I thought that you could even see what constructs the students already know by looking at what they are using in the solution they are providing, right? And based on that, you could even suggest new exercises that they can fill in later. So if you see that a student is using like a more advanced construct, then you can suggest that later. But now, regarding your question about like grading the answers and providing more like tailored feedback, I think we could also use that in that regard, right? Like, so one thing is suggesting exercises, but then in the same way you can say, okay, you're using this construct, maybe you could think about, like improving the implementation by applying the following steps, sort of scaffolding them, like the development and the performance of the student.
Right. Any more questions? If not, then let's thank the speakers again.
Thank you.
And this now concludes the last talk, and I give the floor to Martin.
Yeah, thanks a lot, Mikhail, for being the session chair this afternoon. I thank all the speakers and all the participants here for contributing to such an exciting event. Very grateful to all of you. On behalf of the program committee, I thank you all. And last but not least, I would like to thank the AV team here and all the assistance that we got locally. Thank you very much. Well done. And I hope to see you all at the next SPLASH'25 next year. Bye-bye.